The first day of the conference, but this May 13th, May 14th, or May 17th, May 14th, May 15th, were planned to be the celebration of our great friend Leon Simon's 80th birthday. So we expanded because we could not find any day that people can come for the 50 years of geometric analysis. So we decided we just mix it together. After Leon is a great contributor for geometric analysis, so we expanded from 11 to 17. But formally speaking, today is a day that we celebrate Mr. Leon Simon's 80th birthday, and it will start. And there will be a banquet for his honor for closer friends, not everybody, tomorrow evening. But if a couple of days later, we will have a banquet for the conference, for the big conference. So, well, Leon was my colleague in 1973 in Stanford, right next door to my office. And I harassed him in general every day. I walk across my, office, 382H. I still remember my office. J or H? You're J. So across the office, I learned a great deal about PDE, nonlinear PDE from Leon. I learned nonlinear partial differential equation from my teacher, Morley. But as you know, when you do PDE, the most important part is to actually sit down to do estimate. I learned the estimate from Leon Simon's class, one of the greatest class that I ever learned. We'll see this. He has many lecture notes that you should go to listen to. And also with my friend, Rick Shen. So we start to do estimates. And I learned how to do estimates since 1973. In 1971, I learned from Morley, but more theoretical. And I know how to do it, but never get your hand down to be actually do the estimate. Only after Stanford, I know exactly how to do estimate. And that was most revealing after working with Rick and Leon Simon on the first paper, stability of minimal hypersurface. And that was a really important changing point for my life to know how to do estimate well. Although I independently was doing gradient estimate on harmonic functions, which was actually one of the important changing point for myself. So I'm very pleased that I have a great group of co-workers in Stanford, and well, we have been back and forth from Stanford. I left Stanford in 1980. These two gentlemen stay in Stanford ever since. And then I think about 10 years ago, Rick retired from Stanford and went to UC Irvine and built a great school in UC Irvine. And of course, Rick has the biggest group in geometric analysis. And I'm very happy to see that because formerly he was one of my students. So when you look at the genealogy, I now have a large group of students largely because of Rixian students together. So I was told I'm more than 600 disciples now. So I'm very proud of that. Well, Rick, of course, has done many important works, and especially the famous work on Yamabe conjecture, and the quarter pinching theorem with Simon Brendel. And I think these are all great achievements on top of many other achievements he has gotten. So he certainly is one of the very major founder of geometric analysis. I'm very happy that he come to give this talk. And we are very happy to honor our good friend, Ian Simon, also. So let's have Rick to start.
Let's see, do I hold the microphone? Can you hear me without?
Yeah.
Or do I need it? Is it on? Okay, there. Okay. Okay, well, it's a real pleasure for me to speak at this conference honoring Leon. I've known Leon for more than 50 years as a teacher, a collaborator, a faculty colleague, and most of all, a friend for all those years. He's had a huge positive influence on my life. And he's a great mathematician, but he's also a great person and has influenced very many people in geometric analysis over the years. So it's a great pleasure to be here to celebrate his youth. Okay, so I'm digging up. Does this work? Is it need to be turned on? Okay, I need to use the computer. Okay, so this is one of my favorite old pictures. This is look at all the hair. This is this is Leon and I in Australia, a place called Hanging Rock, which is not so far from Melbourne. It's taken in 1980. So that's the way we looked back then. Barely recognize us, I'm sure. What's that? Handsome. Well, Leon is for sure. Okay, whoops, the wrong way. Okay, so I'm going to now talk about a current project that I'm working on, and it has to do with the relationship between certain eigenvalue problems and minimal surfaces, and it's mainly for two-dimensional surfaces that this sort of relationship is known. And so in certain special situations, so if you look at minimal surfaces in some special manifolds, the equations, the minimal surface equations are actually eigenvalue equations. So the original example of that was minimal submanifolds of spheres. So in that case, minimality is equivalent to the coordinate functions being eigenfunctions for the Laplacian with a particular eigenvalue. And so it turns out in situations like that, the criticality of the area for the surface seems to reduce to the special property of the metric on the induced metric on the two-dimensional surface. And in particular, the metric tends to be a critical point. The metric's a critical point for the eigenvalue in the space of metrics. And so in particular, many of these examples, minimal surface examples, arise as critical points, usually maximizers of a normalized eigenvalue. And so my talk has that theme. So so unfortunately, I don't have very much time, so I can't. The theory in the sphere sort of begins with the Li Yao paper in the early 80s, but it's been advanced much beyond that. So I don't have time to give all the background. So my particular setting will be surfaces with boundaries. So I will give a quick summary of a corresponding eigenvalue problem called the Steklov problem and its connection with minimal surfaces in the ball in round the round Euclidean ball. And then the work was motivated by an attempt to understand a classical minimal surface, which happens to be a free boundary surface in a cube. It's called the Schwarz P surface. So it extends to a periodic surface. And so I'll talk about that. And that actually led to a general discussion of minimal surface and products of balls. So we extended the ball case to products of balls in a general way. And then actually this paper was posted a few months ago, but in the ensuing time, we've gained a much more complete understanding of a special case, which is the generalizations of the Schwarz P surface to free boundary surfaces in rectangular prisms. In R3 in particular, we've proven some multiplicity results, results of multiple solutions, and also an embeddedness theorem for those. So let me first talk about the Steklov eigenvalue problem, which some of you may not be familiar with. So it has to do with the Dirichlet to Neumann map. So if you take a Riemannian manifold with boundary, then the Dirichlet-Neumann map takes a function on the boundary, then you take its harmonic extension u hat, and then the L of u is defined to be the Neumann data for that function. So it takes Dirichlet data to Neumann data for the harmonic extension. It's called the Dirichlet to Neumann map. And so it turns out to be the operator L is a self-adjoint operator, and it turns out to have discrete spectrum. So the eigenvalues for that are called Steklov eigenvalues, and those will be the topics of interest. So this is the self-adjointness, which follows directly from Green's from Green's theorem, and also it's of course a non-negative definite operator, as you see in the last line there. Okay, and so because of the Sobolev space theory, the compactness of the embedding of W12 into L2, it's possible to diagonalize the quadratic form on L2 of the boundary, the L2 functions on the boundary, and the eigenvalues are the Steklov eigenvalues. So there's a trivial one, sigma naught, corresponding to the constant function, and then sigma 1, if the manifold is connected, is a positive one, and then they go to plus infinity. And their eigenfunctions, the eigenfunctions, if we think of them as harmonic functions inside, satisfy the condition that they're harmonic inside and their normal derivative is proportional to the function on the boundary. So the proportionality constant is the eigenvalue. Okay, and so they have a variational characterization, which looks very similar to the usual one. Namely, the only difference, the Rayleigh quotient has the integral of u squared on the boundary in the denominator instead of in the interior. And the critical points of that, so it's a scale invariant quotient. The critical points are the Steklov eigenfunctions. And so there's a min-max characterization or max-min characterization in the usual sort of setting. You find an orthonormal basis of eigenfunctions. Okay, and so let me just mention an example which is somewhat relevant to the minimal surface setting that I'll talk about, and namely the example of cones. So if you look at the unit ball, then of course that's the cone over the unit sphere, and it turns out the Steklov spectrum of the unit ball is exactly the ordinary spectrum of the unit sphere. The eigenfunctions are just the homogeneous harmonic polynomials of degree k, and they have Steklov eigenvalue k. The normal derivative is k times the function. So in particular, the first one, sigma 1, is spanned by the n coordinate functions. And actually, more generally, if you take a metric cone, excuse me, a metric cone, then the Steklov spectrum of the cone is exactly the ordinary spectrum of the manifold you're coning on. So M naught, it's a similar thing. So there's a singularity at the origin, but it's mild enough that it doesn't really affect things. Okay, and so So there's an old optimization theorem about Steklov eigenvalues, which just in a very simple case, but it sort of leads to the general sort of discussion I want to make. And that is, this goes back to 1954. And so actually it's a precursor to a theorem you might know on the two-sphere by Hirsch, which is sort of the starting point of the two-sphere analog of this theory. And it uses complex analysis. So it uses an idea of Zago, really. And what it shows, if you take any simply connected plane domain, then the normalized first Steklov eigenvalue, which is normalized by the length, so this quantity is scale invariant, it's always bounded above by 2 pi, and the equality is achieved only for a disk at any radius will achieve that. Okay, and so let me say that if you replace the disk by any other surface, there is an upper bound on the first normalized Steklov eigenvalue by a constant that depends only on the topology of the surface. So you get this the functional, which is always bounded from above. You take a compact surface with boundary, and that uses fairly well-known techniques by now, which I won't go into. But then what we're interested in, of course, is the best upper bound, or actually maximizing in general. And if we so let me now come at it from the minimal surface point of view. So we can think of the disk as sort of a trivial minimal surface. We could put it in the 3-ball if we want, and it would be what's called a free boundary minimal surface. It meets the boundary orthogonally. And more generally, if you have any minimal submanifold of the ball, the unit ball, say, which is proper, so the boundary is contained in the boundary of the ball. If it's free boundary, that means it meets the boundary orthogonally. So that's the condition that the outer normal vector for the surface is the position vector on the sphere, and that condition just reduces to the statement that so the outer normal vector, of course, is the normal derivative of the position vector itself. And so it just reduces to the statement that the coordinate functions are Steklov eigenfunctions with eigenvalue 1. So the harmonicity inside is just the minimal surface equation. And so those are so that's an example where Steklov eigenfunctions arise directly. Okay, and so the statement is that it's a free boundary minimal surface in a free boundary, M is a free boundary minimal surface in the ball if and only if the coordinate functions are Steklov eigenfunctions with eigenvalue 1. Okay, and so then you can ask the question about maximizing sigma 1L. So it's bounded from above, so you can maximize. There's this general theorem that says that if the maximum exists, then in fact there's an immersion, possibly a branched immersion, of the surface into a ball. We can normalize it so it's the unit ball, and so that it's embedded or immersed by first Steklov eigenfunctions. Okay, so that's a general. It's if you like, it's computing the Euler-Lagrange equation, but the point is eigenvalue is not a smooth function because of multiplicity. So there's some work involved in showing that, although it's quite analogous to a similar result in the sphere that I alluded to but didn't really describe. Okay, so in particular, what it says is that the minimal free boundary minimal surfaces tend to arise as maxima, or maybe more generally critical points of a normalized Steklov eigenvalue. And so that's the basic principle I want to push. So let me just mention a couple of easy examples. So this is the Weinstock ones. It's the disk, and so this turns out to be the flat disk through the origin. Turns out to be the only simply connected free boundary minimal surface in B3. It's actually also the only one in Bn for larger n, it turns out. And then the first sort of non-simply connected one is the critical catenoid, which is the piece of the catenoid which meets the boundary sphere orthogonally, and then you can scale the catenoid to make that a unit ball. So that's called the critical catenoid. And there are various questions about how unique that one is as well, which are not known. But let me just say, generally, Fraser and I in our paper looked at constructions of genus zero with arbitrary many boundary components. And in quite recent work over the last few years, there's a paper of Karpuk, Kusner, McGrath, and Stern, where they constructed arbitrary topological types. So they used eigenvalue maximization with symmetry. So this idea of using the eigenvalue characterization to find minimal surfaces turns out to be quite productive. And so there are also other, in the reverse direction, questions about for a minimal surface, the behavior of in particular, the first Steklov eigenvalue. Okay, so that's a quick rundown on the relationship between the Steklov eigenvalue problem and free boundary minimal surfaces in the ball. Okay, so there's another classical minimal surface called the Schwarz P surface, which I have a picture of here. It's actually a triply periodic minimal surface, and the basic piece, it's a little hard, maybe it doesn't look quite right in this picture, but it's actually a free boundary minimal surface whose boundary lies on the boundary of a cube, and it's of a special type in that the surface does not contact the one skeleton of the cube. So so each boundary component of the surface is contained in a face of the cube. And so I have a little better picture on this slide. So so it was originally constructed by reflecting a suitably chosen minimal disk with polygonal boundary and constructed, I think, by Schwarz in the 19th century. I have to confess, I haven't looked at the original paper, but Cho, my co-author, is familiar with that. But let me also say then, so our goal was the question was, is there an eigenvalue theory which somehow characterizes free boundary minimal surfaces of this type? And in particular, understanding it in more analytical terms would possibly allow generalizations. For example, whether such surfaces exist in rectangular prisms with unequal side lengths. I gave this talk, a similar talk, a few days ago in Japan, and it turns out that someone in the audience, Miyuki Koiso, had written a paper using complex analytic techniques to understand extensions of the Schwarz P surface. They were able to write down a Weierstrass representation and deform it to produce some examples in other rectangular prisms. In particular, they seem to be able to get the ones with two equal side lengths using that. So it's I made the slides before I knew this paper. So so there has been work from a different point of view. Of course, two-dimensional minimal surface theory is closely related to Riemann surface theory, complex analysis, and so there is an approach also from that point of view. Okay, and so so in order to understand this from an eigenvalue point of view, we first have to understand whether the coordinate functions on the Schwarz P surface satisfy. Let's see, I go till 10:15, right? Yeah. Okay. Yeah. So we first have to understand whether the coordinate functions satisfy eigenvalue conditions, and it turns out they do, but they're not the same boundary conditions for each coordinate function. So what happens is if you take the ith face of the cube, so that is the face perpendicular to the xi axis, then on that face, the coordinate function xi, that associated coordinate function, is Steklov. It satisfies the condition that I'm considering here a cube of side length 2a, so minus a to a, so it's centered at the origin. Then the Steklov eigenvalue for xi is a to the minus 1, as it would be if I took a ball of radius a instead of a ball of radius 1. And so that first one, the xi, looks a bit like the ball case, but the other two coordinates, xj for j different from I, are Neumann. They satisfy the Neumann boundary condition. So it is true that xi satisfies an eigenvalue condition, but the condition is that it's Steklov on the pair of boundary components perpendicular to the xi axis and Neumann on the other two. Okay, and so it's a mixed Steklov-Neumann boundary condition. Okay, and so so then we ask the question, well, is there some way to formulate a variational problem for mixed Steklov-Neumann eigenvalues whose critical points would produce something like the Schwartz P surface, or more generally, we could ask this in general. And so of course, the rectangular prisms are just product domains. They're product of one-dimensional intervals. And so it turns out the generalization that follows from this is a general construction of free boundary minimal surfaces in products of balls. And so the idea is that we can understand the Schwartz P surface by taking its 6 boundary components and separating them into three groups, where each gamma I corresponds to the faces perpendicular to the xi axis. Okay, and so then the boundary conditions on xi is then Steklov, and it's Neumann on the other two. So that's the setting. And so if then we ask what's the right functional for this problem, well, we can imagine that we have a conformal embedding of some domain surface into R3, which parameterizes the Schwartz P surface. Then if we write the energy, which is, of course, twice the area of the embedding, then that's just the Dirichlet energy, and then the U's are harmonic. So we do an integration by parts, and then using the fact that Ui is plus or minus A on the components in gamma I, we can see that this sum is a sum of A squared times, these are just normalized eigenvalues. So sigma I is not a Steklov eigenvalue, but it's the mixed Steklov-Neumann eigenvalue associated to the ith pair. And so so that's what the functional looks like, and that leads to if we take a compact surface M with B boundary components, 1, and if we divide them into K different, so call those gamma 1 up to gamma K, each one is non-empty, and it includes a certain number of the boundary components, and they're also disjoint, of course, of M. And then we can then associate it to each gamma I. We can look at the eigenvalue problem. It's called SN Steklov-Neumann sub I. It's the eigenvalue problem where the eigenfunctions are Steklov on the boundary components in gamma I and Neumann on the others. And so that's a good eigenvalue problem. Again, it's associated to a Rayleigh quotient, where now the difference is that the denominator involves only the integrals over the gamma I. So this is so the other gamma J's are not there, and that's reflects the fact that we're imposing Neumann conditions on the other gamma J's. And so but the problem still is good as long as the gamma I is non-empty. It has a discrete spectrum. The lowest eigenvalue 0. The next one's positive. We can look at the first non-zero eigenvalue, sigma 1 upper I. Okay, and so then if we fix positive numbers A1 up to AK, we can then consider the functional. So this functional is a weighted normalized sum of the Steklov-Neumann eigenvalues. So again, we normalize not by the whole length of the boundary, but only by the length L sub I, which is the length of those components in gamma I. Okay, and then we can ask. So it's again similar methods can be shown that this is bounded from above over the space of metrics on the surface, and then we can ask for a maximum. So actually, if we could construct a maximizer, then we've proven that the corresponding for that maximizing metric, the eigenfunctions would produce a free boundary minimal immersion into a product of K balls of the given radius. So we're allowed to specify the radii in advance in the construction. Okay, and so we get that. On the other hand, there's some bad news in that it turns out in many cases you can't maximize the problem. So what happens is a maximizing sequence would degenerate. So for example, if you just look at one of these things, Li of G sigma 1I, you can find an upper bound on it by shrinking all the other boundary components to points. And when you do that, because of the Neumann boundary conditions, it turns out the normalized eigenvalue goes up. See, the length doesn't change because I'm only computing the length on the gamma i's, but the other lengths go to zero, and because of the Neumann property, you get increasing. So there's an upper bound on each individual term, and then when you do the sum, if you allow arbitrary metrics, you can choose metrics which sort of separate those into, so they're sort of infinitely far apart, and you can show that the maximum generally doesn't occur. Well, we at least did it for genus 0, so that it's in the paper. We don't think it can be maximized in general, but quite have a proof of that. So, but in any case, you don't expect the existence of a maximizer. Okay, so what's the way around the problem? Well, so the Schwartz P surface has a lot of symmetry. It has the symmetries of the cube. So we might then expect to restrict our optimization problem to metrics which have some symmetry. So we would like to assume as little symmetry as possible. So we need enough symmetry to make it work. On the other hand, we want to impose little enough symmetry that we get lots of examples, lots of instructions. So it turns out the right thing to do after some experimentation is to just impose the 3 reflection symmetries. So you you just look at solutions that are invariant under reflections through planes which permute the boundary components in gamma I. So rho is in gamma I, and it preserves, not pointwise, but it preserves the other two components. Okay, and so then there's a very general theorem. It's kind of wordy, so let me just say the general theorem. I'll just say it in words: is that if you impose a finite group of symmetries on your metrics under consideration, and assuming you have surfaces which have those symmetries, of course, then if you can maximize the eigenvalue problem over symmetric metrics, then the maximizer will produce an immersion into a product of k balls of radius, of dimension, which is not specified in advance, so the n1 up to nk, and then they're of radii ak, and the immersion is equivariant. So there's a representation of G in the product of the orthogonal group so that it's equivariant. So this is a general, if you like, Euler-Lagrange condition. So we can impose symmetry, and if we can maximize it, then we will produce our free boundary surfaces. Okay, and so we're going to apply this in the special case of a genus 0 surface with 6 boundary components. So we divide them into 3 groups of 2, gamma 1, gamma 2, gamma 3, and then the group is Z2 cubed, and the rows switch the 2 boundary components, preserve the other components. So a topological model is just the 2-sphere with a disk removed at the 6 points where it intersects the coordinate axes. Right? And so that's a topological model. Then the reflections would just be realized by reflections across the coordinate planes. Okay, and conformally, we can also understand the moduli space of these conformal structures very explicitly. Namely, it's a genus 0 surface, so it can be holomorphically embedded into S2 minus round disks. So this is a classical uniformization result. And because of the symmetries, you can then show that any such surface is holomorphically equivalent to the 2-sphere minus disk of equal radii at the points, the plus and minus points on the axes. So they're really parameterized by 3 numbers: R1, R2, R3, which are the radii of the disks that you cut out on the. So Ri is radius at the 2 points on the ith axis. And so there are 3 numbers that parameterize the moduli space, and they satisfy certain inequalities. Well, first of all, they're positive, so that you're cutting out some disk, and the sum of any pair is less than pi over 2 for I naught j. So that's just the condition that the ith and the jth disk don't touch each other. So it's an embedded domain in the sphere. Okay, and so right, and so the strategy of the proof, which is sort of a common strategy in these 2-dimensional problems, is to first fix a conformal structure. That means we fix a point in the moduli space and then do the maximization. So it turns out that actually can always be done even for this functional f. And then the idea of studying the behavior over as we vary points in the moduli space. Okay, and so it's actually a locally Lipschitz function in general. And it turns out, in this case, bounded from above, it turns out it actually extends continuously to the closure. And so we can maximize on the closure. And then the key argument is to show that maximum point actually occurs in the interior. And so the way of, so actually it's sort of interesting how the mixed conditions are used. It's actually very important in doing that to know that if you take any 2 boundary components that come together, there is one of the eigenvalue problems for which both of those are Neumann. So it turns out when you have 2 Neumann components stretching, if you move them apart, you get an increase in the eigenvalue. So the exact configuration here seems to be quite essential. It wouldn't work, for example, if we only had 4 boundary components grouped into pairs of 2. Then it would degenerate. In fact, the solution doesn't exist in that case. So okay, and so let me just say that the problem is, so we get a general maximization theorem, but the problem is we don't actually know that we produce the Schwartz P surface or anything that looks like it, because it's possible that these surfaces actually immerse into higher dimensional spaces. So in general, you don't specify in advance the dimensions of the balls that you're considering, and so for this particular eigenvalue problem, the maximum multiplicity is 3. So it's conceivable that the minimal surface actually lands in R9 if all of them were 3. So and so we don't necessarily, even if we choose all the A's to be the same, we don't know whether the surface we produce is actually the Schwartz piece, or it may be in a higher dimensional space. And so if we took all of the A's to be equal, we could then impose further symmetry, which permutes the radii. So then we get a 1-dimensional moduli space. So it turns out that you can check that f is actually 0 at the endpoints of the interval. And so you can certainly maximize f. But even in this case, it's not clear that the surface lies in R3. Okay, so I'm a little short on time. So let me now explain how we can get these into R3. And so the idea is to restrict the problem even more and to look at so generally there's this involution that permutes the 2 boundary components. So we can look at eigenfunctions which are either even or odd with respect to the involution. And it turns out the odd ones, the first odd spectrum, the odd eigenvalues, actually the first one has multiplicity 1. So that's actually makes things much nicer. And then we can then define the corresponding functional, where instead of taking the first non-zero eigenvalue, we take the first non-zero odd eigenvalue. We call that f sub o, f upper o, means corresponding to odd. And then we can again attempt to do it. Now, one catch is that when you restrict to odd eigenvalues, you lose the upper bound. So in fact, it turns out to be a good thing for us. The functional is no longer bounded from above. You can sort of see that because if you took a situation where one of the radii goes to pi over 2, so then the surface looks like a pancake and you have the other radii are very small, then if you're taking odd eigenfunctions, the eigenvalue has to go roughly from -1 to 1 in a very short distance. So you would expect the eigenvalue, the odd eigenvalue to be very large in that case. And indeed it is. And so actually, we can analyze this situation somewhat more explicitly. So we can explicitly describe the maximizer in a conformal class. And so the way we can do that is, again, it's because of the multiplicity one condition. It's a very simple setting. If we take the harmonic function, which is +1 on one component of gamma I and -1 on the other, and Neumann on the other 4 boundary components, then this function, AI ui, is actually the first odd eigenfunction for Sni, but with respect to a metric that just depends on the normal derivative. So we just define the metric, so it's an eigenfunction. And now the thing you can show fairly easily is that the metric actually maximizes in its conformal class. And then if we compute the corresponding term in the sum for the functional, we just get the Dirichlet integral of that function. Okay, and so in particular, the FO, the odd eigenfunctions, the functional we're considering is exactly equal to the energy of P. So E is a function of P, and it's the energy of this map. So we're specifying the A's, remember, so we take A1, U1, A2, U2, A2, U3, and the UIs are just plus and minus 1 at the opposite components of gamma I. And so then we come upon a more classical problem of trying to find critical points for the energy on a moduli space. And those, again, would produce minimal surfaces. And so in the paper that's posted, we showed that there exists for any choice of radii, A1, A2, A3, there's a free boundary minimal immersion into the rectangular prism. So we get a Schwartz P-type surface for any A's. And again, the proof, so it turns out on the boundary of the moduli space, there are exactly 3 points where the energy blows up. And those are the points where one of the radii goes to pi/2 and the others go to 0. So you get these 3 points. And so in particular, if you consider the points where the energy is very large, there are 3 components. There will be a component near each of those points. On the other, if you consider the points where the energy is very small, then it turns out the super level set is connected. So whenever you pass through a point where the number of components changes, you expect a critical point for the energy. And of course, the problem is that you need to show that the critical point lies in the interior, right? And so again, the analysis for that is somewhat similar to the previous one for maximizing. And so you can show that. So in other words, you can show that the gradient of E near the boundary points into the moduli space. And so, okay, and so let me now briefly describe the new results. So based on this picture that you're going from 1 component to 3 components, you expect 2 critical points. Okay, and so in fact, we can prove that. We can show that it doesn't use Morse theory, it uses the special structure, the symmetries of this space. And so we can show that actually if they're not all equal, then in fact you get at least 2 surfaces of this type. And so the idea, the proof involves exploiting the asymmetry of the energy function under permutations of the radii. Okay, and so there are various monotone properties of these associated energies when we change the radii, so in other words, we can construct the critical points by looking at max-min paths, and we want to show that if the A's are not all the same, at least 2 of those are distinct. So that's sort of generally the idea, and it comes from using these involutions which switch the boundary components to show that if you had only 1 critical point, you could up the path. You could violate. So I'm running out of time here, but anyway, so there are arguments like this. If you had a point, if AI is less than AJ, and if you have a point where, say, RI is bigger than RJ, then by looking at the point which switches I and J, you increase the energy. Okay, so it uses those kinds of things. We also have to worry about cases where the radii are all equal, but it turns out they can't be all equal unless all the A's are equal. So there's an analysis to do that. Okay, and so maybe I get the proof. So okay, so that's one result is the existence of at least two solutions. And the other result's embeddedness. So these a priori are just conformal harmonic maps. So to get the embeddedness, we sort of show that these surfaces have a similar property as the Schwartz P surface. Namely, if you think of the Schwartz P surface, if you cut it with a plane, which is say horizontal in this picture, then the upper half and the lower half are both graphical. Okay, and so what we can prove in general for any surface with these symmetries, the embeddedness theorem. So if you take an immersed free boundary minimal surface genus 0, a boundary component on each face of a rectangular prism, if sigma is invariant under the three reflections, then actually it's automatically embedded. So we can make the argument that that it's a union of a pair of graphs which meet orthogonally at the boundary. Okay, and so just a summary of the results. So by the way, the paper is written and it should be posted within a week or two. And as I say, the first paper is already there, but it only constructs one minimal inversion. Okay, and so given three positive numbers, there's at least one embedded free boundary minimal surface of genus 0 with one boundary component on each face. If the prism is not a cube, then there are at least two. So that's the general result. Okay, so I'm out of time, so I'll stop there.
Well, so a great talk as usual. So let's see whether the questions. Yeah.
My question is that in the degeneration toward the critical catenoid limit, is there a more precise blow up or bubble tree description of the neck region? Thank you.
In the degeneration for the critical catenoid, let's see, how is the critical catenoid degenerating? Are you thinking of a rectangular prism, which? Oh, okay. So I'm not sure if you get the critical catenoid in any limit. Yeah, I thought a lot about, a bit about what these solutions look like geometrically. And I think it's probably true that if you take a very flat, so you fix two of the sides, take them fixed, and you let the other side go to 0. I thought the picture should be a little bit like the way the two nearby circles has a pair of minimal surfaces, the unstable catenoid and the stable catenoid. So my guess is that when you do that, the limit will actually be when you let it go to 0, one of the solutions will converge to a double disk, and the other one I think will evaporate, will go away because the area goes to 0. I don't really know how to get the critical catenoid in the limit of these because the boundary is polyhedral. So I don't know if there's a limit that produces that.
Okay, other questions? Other questions? Well, actually, I have a question. It's somewhat related to what your talk is, but not exactly. So many years ago, about 25 years ago, I wrote for the IMU lecture for the centennial thing.
Mm-hmm.
So I asked the following question: given a domain in R field, in general Rn, you have eigenvalues, Dirichlet or Neumann, and then you have the eigenvalues on the boundary surface. I was trying to relate these two sets of eigenvalues.
Right.
Now that listening to your lecture, one should add the stack of eigenvalues. So these three sets of eigenvalues, are they linked together in some way? So that means, for example, if I know all the eigenvalues in the interior, all the eigenvalues of the stack of problem, could we determine the eigenvalues on the boundary?
Of the other one.
on the boundary surface. I think this free set
Yeah,
eigenvalue
interesting question. I
should be interesting. Maybe one can study.
well, I
that.
mean, I guess if you know all the eigenvalues in the interior, you might expect to know the domain, at least
Yeah,
generically.
but I want more
Then
explicit
you want to know, yeah.
relation. So that
We're going from one to the other.
Yeah.
I think there might be inequalities.
Well, I broke down
things,
inequality.
yeah.
Actually, a nice inequality.
Right.
Relating eigenvalues only in the interior.
So asymptotic for large eigenvalues, or
yes,
actually there are even some for all eigenvalues, right?
It's actually
Right.
inequality.
Yeah, right. Yeah, I don't know. It's a good question.
Well, it could be related to the minimal surface. I don't know. Anyway, are there more questions? If not, let's friend Rick. What's the second agenda? Oh, okay. Oh, yeah. Okay.
Hello, everybody. Good morning.
So we have Professor Dileras joining us from far away, from Princeton IAS, and oh, he's in Italy. Sorry.
Yeah, actually, I'm in Italy. Yes.
You are professor in Princeton. This is a major conference in celebration of Leon Simon's 80th birthday, and minimal submanifold is clearly the major topic. And Leon has been working on singularity or minimal submanifolds, and this is one of the very major achievements in the 20th century and pushing on up to now. And of course, Professor Dileras is one of the chief contributor to this subject, especially only through his hand, we understand the deep work by Freddie Unger. So we are very proud of his achievement, and I'm very happy that he will join to give this talk here online. So let's start.
Thank you. Thank you very much. I'm sorry I cannot actually be there, but I'm holding a series of lectures, which I promised to give actually long ago. So let me try to see. I should share, and you should now be able to see my slides, and I'm going into full screen mode. Okay, let me actually get this away. Okay, let's see. Yes, right. So the title of my talk is Boundary Plateau Laws, and I will actually explain a work which I have been doing since quite some time with Federico Glaudo, who was up until last year postdoc at Institute for Advanced Study. So, okay, I shouldn't actually explain the plateaus problem to this audience, but anyway, let me remind it what it is. So given a one-dimensional contour gamma in the three-dimensional space, I want to actually find the surface sigma of least area which spans it. And even though it was actually first proposed by Lagrange in 1760, it's named after the Belgian physicist Plateau, because he actually proposed it to model the shapes of soap films in the 19th century. And of course, the experiment that we all have in mind is the one of taking a wire, dipping it in a bucket of soapy water and pulling it out, right? And this is one nice picture that I can actually find on the web. And, you know, in these times, you're not always sure whether this is actually AI generated or an actual experiment. But anyway, it looks nice. Okay, so in the 19th century, Plateau formulated what are called the Plateau laws, which, roughly speaking, you could formulate in this way. So if you are at the point P, which is away from the wire, then locally the film looks like either a smooth surface or like three smooth surfaces which are coming together at a smooth line forming equal angles, or like a smooth deformation of the cone over the one skeleton of a regular tetrahedron. Actually, I'm saying smooth, but C1 or C1 alpha is what we're really looking for. And one should also be aware that even though I can deform, there are some extra rigidities because actually the angles have to be preserved. So I cannot move like the angles between the three smooth surfaces which are coming at the same line in the second example. And similarly for the tetrahedron. Okay, so these are actually the three models. So you see on the left, with my little end hovering over the flat plane, the three half planes which are coming together at a common line. And here it's perhaps a little bit more difficult to decode, but this is like, thick. Over here, I have the skeleton of a tetrahedron, and here in the middle, I have the central point, the barycenter of the four vertices of the tetrahedron, and then I build the cone over it. So these are the three models which exemplify the plateau laws. Now, these plateau laws were actually translated in the 1970s by Gene Taylor into a theorem about area minimizing surfaces. So one way to phrase the theorem is the following: assume you have a closed set E in R3, and assume it minimizes the two-dimensional Hausdorff measure with respect to a certain boundary gamma, but in the following sense, which was proposed by Almgren back in the 60s, I believe. So what you actually want is that the Hausdorff measure of the set E is always less or equal than the Hausdorff measure of any Lipschitz deformation of this set. And this is actually for every Lipschitz map phi, which satisfies two constraints. It does not move gamma, so which means that it is the identity in the neighborhood of gamma. And it does not move anything else on gamma. So technically, this means that all of the points which are displaced, which are away from gamma, cannot actually be mapped onto gamma. And in fact, you need to leave a little bit of space. Like you want actually these images to be at positive distance from gamma. Now, why actually Almgren minimizers? So there are several proposals of what it means for a film to span a contour gamma. So for instance, one could ask, why don't I take just simply every smooth surface, oriented smooth surface, which actually bounds the contour gamma if gamma is a curve? Well, one of the reasons not to do that is because the powerful regularity theory, which was developed in the 70s and completed at the boundary actually by Leon and Bob Hart, tells you that in that case, the minimizer is smooth up to the contour. And we know from the examples that there are, in fact, singularities in the actual experiments. So if you want to describe soap films, you want a notion which is general enough to actually allow for the singularities. Starting from the work of Reifenberg, there have been several proposals on set theoretic ways of defining what the minimum is. But one nice thing is actually that this Almgren minimizing condition seems to be actually shared by all of these other frameworks. So if you prove a regularity theorem or a classification of singularities, which is actually valid for Almgren minimizing sets, then actually that classification is going to be valid for any minimum in any of the formulations above. At least, say, the worst thing that could happen is that there are even less singularities than what you are able to describe for Almgren minimizing sets. Okay, so here is actually a formulation of the theorem by Taylor. If E is Almgren minimizing two-dimensional in R3 with respect to some boundary gamma, and P is not in gamma, then in any sufficiently small ball centered at P, the set E is diffeomorphic to one of the three models in the plateau laws. So now the question of my talk is what happens at the boundary? So pick a point P in gamma, and you might ask, is there a similar description of the possible shapes of E at the point P? And let me make two assumptions. So one first assumption is that gamma is a regular curve at P. So in first approximation, of course, you want to understand the situation in which you have enough smoothness. Let me denote by L the tangent line at the point P. In fact, we don't need that much regularity, but at least differentiability is important. Then you have a theorem by Allard, which actually tells you that since this set E induces a stationary varifold, then around the point P, you have a monotonicity formula which tells you that the rescalings converge to cones. More precisely, if you pick any sequence of radii Rk, which is going to 0, and you center the point P at the origin and then rescale homothetically by a factor 1 over Rk, then these sets are converging in the Hausdorff sense, for instance, to an angular minimizing cone with respect to the boundary L. But you have to pass two subsequences because you don't know that actually the limiting object is unique. Well, this means that in first approximation, you can ask the question of classifying all closed sets E in R3, which of course at this point are cones, so it means they are invariant under dilations. Since we actually have infinite objects, we want to kind of impose that the two-dimensional area of the intersection with the ball, say, is finite. I mean, this would come actually out of Adler's theorem automatically. And then, because in the blow-up procedure, your curve gamma is going to look more and more like its boundary, its tangent line at the point P, which is this line L that we have fixed, then E must be angular minimizing with respect to the boundary L. So your deformation phi's, which are actually allowed to test the minimality of the set E, cannot touch this line L in the sense that we specified before. Now observe that because E is a cone, there are in fact three possibilities between these two sets, E and L. So E intersected L could be the origin, in the sense that after all, the set E actually is not wetting the boundary at all, only just passing through that point. The set E intersected with L could be a half line, so E is only wetting half of the line, or actually the line L could be included in the set E. So the concept of angular minimality doesn't really specify how this boundary data is achieved. So any of these three possibilities actually is in principle allowed. Of course, the one which I've actually highlighted in red is in principle the most interesting one, certainly the first one that you want to understand, because even though when you run experiments, you can see that there are soap films which do not attach to the complete wire, most of the times actually the soap film is attaching to the whole wire, is wetting the whole boundary gamma. And so the red one is actually the most interesting case, and in the blow-up procedure with which you actually get cones, if a priori you have an information which tells you that your initial set was in fact wetting all of the wire, then the cones are going to do that too. Okay, so this is actually the theorem that I have with Federico when I'm saying it's forthcoming. We're, I guess, like a month or so away from actually putting this on the web. The proof is all written down, but it's pretty long and convoluted, and so we're just proofreading actually our manuscript. So if you have a set in R3, which is an angular minimizing cone with respect to this line L, and you assume that L is inside E, in fact, I can actually tell you the information that E belongs to one of the following 6 families of cones, and I'm going to give you a pretty good description of them. So note that this is not an if and only if. So what I'm really telling you is that E must belong to the 6 families of cones, but we don't have a theorem which is actually saying that all of them must be minimizing, which would be the correct counterpart, if you want, of the first part of Taylor's theorem. Also, I'm not telling you that when you see one of these tangent cones, the set from which you actually made the blow-up has to be diffeomorphic to it at a certain sufficiently small scale. So these are actually questions which seem rather challenging at the moment. So let me give you the list. So there are 3 which you could easily imagine. So the line L is depicted in red, and of course you could have a cone which is just a half plane bounded by this line L. You could have a cone which is the union of 2 half planes actually bounded by the line L, but in this case you see that the opening angle is going to satisfy a condition. So it has to be at least 120 degrees. It could be more than 120 degrees though. And then you have the situation in which you have a triple junction like in the interior, and your line, your red line is actually passing exactly through it. Now these are all minimizing. In fact, the the first and third are kind of obvious. For the second, like, you have to write down a little argument, but it's a very short and it's very obvious argument anyway. Now, another thing that you could actually notice is that if you take the other cone, which is minimizing in the interior, which is the tetrahedron, the cone over the one skeleton of the tetrahedron, actually this cone contains 3 lines which are passing through the center. So here you see one line. If you take a midpoint of one edge and you take a midpoint of the opposite edge, then the line connecting it is the line passing through 2 heights of 2 of the triangles which are forming the cone. And so obviously this is also an example for which we know that it is minimizing, because it is minimizing in the interior. And so it's one of the valid geometries. And it is minimizing. Now here there's a more interesting example. So this doesn't appear in the interior. So you could be the skeleton over a one-dimensional cone. And in this case, of course, because the cone is symmetric with respect to the origin, there's infinitely many lines which are contained in it. So for instance, one could be the diagonal. But then you could actually move the diagonal and slide it until this red line becomes the line which are connecting 2 opposite edges. Now, what we actually can say is that this example is certainly not minimizing if the point P that you see over here is a midpoint of the edge. And because minimizing cones actually form a compact set, this also means that if I am just close to the midpoint, then I cannot be minimizing. So on the other hand, there are actually very strong indications, I will show them later, that the one with the diagonal is minimizing and that the ones which are sufficiently close to the diagonals are minimizing. Then it gets even more interesting with the 6th family, because this is not something that, oh, by the way, so this is a little experiment which shows you that the cube with the diagonal is potentially is potentially minimizing. So you see that the diagonal over here is a thin string. So one of the reasons why I actually made the experiment with a very thin string is because one could actually be worried that the thickness of the boundary might influence. I mean, for instance, if there's a little opening here in the origin, if you take a thick segment like this one at your relevant part of the boundary, maybe you believe that something is minimizing without it actually being very minimizing. But okay, apart from the experiments that I ran with soap films, which maybe not being a professional experimental physicist are not so reliable, one has to say that numerical simulations actually give strong evidences that the cube is minimizing. Okay, this is the last geometry, and it's something new and more complicated, although it is actually a fairly, it is actually a surface with fairly small area. So in this configurations, you have to imagine you have these points P1 and P2, which are on the sphere, and they are antipodal. These are the points through which actually the boundary line is passing. And then you have 4 other points, V2, V1, V3, and V4, which are lying on the sphere as well. Instead of actually drawing the geodesic arcs connecting them, I'm drawing straight segments because it's easier to visualize. But of course, the cone is agnostic actually to that. So now these V1, V2, V3, and V4 are actually 4 points of a cube inscribed in the sphere. And the 4 edges that you see over here are the 4 edges of the cube. But then there's another edge, which is actually this geodesic arc, which you have to think is like a geodesic arc of the sphere, which is a non-length minimizing geodesic arc. So you're like going around in the opposite direction than you would take if you were to take the diagonal between V1 and V3. And of course, these angles over here are 120 degrees. And then there are these two arcs, gamma 6 and gamma 7. And of course, these arcs actually, they meet the other two segments at the point V2 and the point V4 by forming 120 degrees. And you make both of them long in such a way that these 2 points, P1 and P2, are antipodal. And you see that there is a degree of freedom because I can make this gamma 6 or this gamma 7, for instance, almost long 0. So if P2 is going to coincide with V4, then I'm actually making gamma 7 of length 0. Or I could take it as long as I am allowed until gamma 6 on this other side actually becomes trivial and P1 is going to coincide with V2. So like for the cube, it's a one-parameter family of different cones. I mean, and when I say different, is like they're not isometric to each other. Okay, so we actually conjecture that these are all minimizing. Of course, in the case of the cube, a plausible conjecture is that there is a critical location for the line, for the red line, which is going to discriminate between the minimizing cases and the non-minimizing cases. And the experiments are remarkably robust. So here is another experiment that you can see in which I'm actually plugging in a model for this final family that I have found. So you see over here that this is again a thin string, which is the the boundary line, the red line in the pictures, and maybe you can see that there is the four flat surfaces which are attaching to the four edges of the cube, and then there's actually another one which is going around, which is a little bit more difficult to visualize. And you can see the same experiments from another side. This is a third one, and this is actually one of my lab assistants. Okay, so now what about the proof? Well, the proof is not completely satisfactory because it actually combines a rather long theoretical part, but it's not so much the length, which is anyway kind of bulky, but it's also the fact that we need the assistance of a computer, and in fact, many lines of code to actually complete the proof. We also use several tools, so it was actually a lot of fun to prove these theorems because the proof finally involves spherical geometry. We had to learn graph theory, Lie group theory, isometries of the spheres actually play a very important role. At a certain point, we had to actually fool around with computational algebra and Grobner basis to solve very large polynomials. And to complete the proof, there's actually also a lot of low-dimensional topology, in particular, topology of two-dimensional simplices, simplicial complexes. And of course, there is a lot of geometric measure theory, as one could imagine. And we face, besides computational challenges, meaning that not only we use a computer, but the first attempt to get the computer to complete a proof failed miserably because we were either requiring too much computational power or too much memory. So we really had to actually understand how to make things in an appropriate and sort of optimized way. But now actually the code doesn't run for a long time. I mean, maybe a few hours on a laptop, so it's easy to reproduce. Okay, so let me give you an idea on how you actually want to prove this. So first of all, there are some very easy theoretical considerations. Because you know Taylor's theorem, you actually know that if you take the link of the cone is going to be a geodesic net. And this geodesic net actually consists of pairwise disjoint geodesic arcs. And they connect vertices. And there are two special vertices, which are antipodal, which are the intersection of your sphere with the boundary line. And at these antipodal points, at least one and at most three arcs arrive. But all of the things could happen. It could be that there are 1, 2, or 3 arcs arriving at them, as you actually saw in the examples. And if 2 arcs arrive at plus or minus p, then they actually have to form an angle which is bigger or equal than 120 degrees. In particular, if 3 of them arrive, actually all of them have to form angles which are exactly 120 degrees. Then there are, of course, many other vertices, and these are all vertices of degree 3. There are always 3 arcs arriving to them, and they always form equal angles. Okay, so now, if you removed actually the points p and minus p, and so you wanted to classify the situations of, say, stationary cones or like, geodesic nets with this particular property, then actually this was done by Aladar Epes prior to Gene Taylor's work. And in fact, there was even a prior work by a student of Plateau who claimed to do the same thing in his PhD thesis in the 19th century, but as it turns out, at least at some point, the proof of the student of Plateau, Lamarle, has to be wrong because Epes has more nets than Lamarle. And so Lamarle actually missed 1 net. So Epes in the 50s classified all of these beasts, and there are actually 9 of them. And he uses spherical geometry and very clever inequalities and clever symmetry considerations. And the proof is extremely elegant. It's actually quite remarkable because he doesn't make a single computation during the proof. So it's all about monotonicity of angles and symmetry considerations. It's really remarkable. Also, each of the 9 examples is actually rigid up to symmetries. And you see that this, we know from the examples that I already gave you, which certainly satisfy all of the prescriptions before, even if you don't believe that they're minimizing, that this cannot be the case when actually there are these boundary points p and minus p. So things are more complicated. Now, of course, most of these 9s are not minimizing because after all, Gene Taylor's theorem actually tells you that there are only 3, so 6 of them are not minimizing, and this was proved in the paper by Gene Taylor. Now, if you compare actually to our case, we have around 30 distinct topological types of them instead of 9. And some of them actually are not rigid. And in fact, quite a few come with 1 single free parameter, like the family number 6, which I actually showed you, which we call the thin fish family. But there's even a nasty one which actually comes with 2 free parameters. Okay, so while actually trying to prove this classification, we found around 20 of them with pen and paper considerations. And I think, a little bit more than 20. At a certain point, I was convinced I got them all. But when we actually started understanding how to, produce software which would allow us to find them or prove that they don't exist with a certain given topology, the computer actually found some additional examples. And so some of them, they're really being suggested by simulations. Okay, so this is actually one of the beasts which have 2 parameters which are free. So this is just a picture of all the arcs on the sphere. I'm not going to describe it, it's just for fun, but the 2 degrees of freedoms are the length of this arc V1, V5, which is on the same equator as V3, V6, and the length of this arc P1, V2, which is on the same equator as P2, V4. It's actually a modification of the 6th family, which I showed you in the theorem. Okay, so how do you actually start getting these 30, which are, if you want, stationary cones? I mean, in reality, just 6 of them are going to be minimizing. Well, first of all, there are very simple topological considerations where you leverage Gauss-Bonnet, which show that there are only finitely many topologies for the links of these cones. Now, the first thing that we wanted to do is actually to derive a code which takes the conditions from Gauss-Bonnet and gives you a possible list of all topological graphs on the sphere which satisfy these conditions, which help us actually prove that they are finitely many. So if you want, we wanted to pass from a proof of finiteness, which was just conceptual, to a way of getting a complete list of them. And of course, we need a theory, so a proof that the topology of any minimizing cone must be in the computer-produced list, and this requires essentially to study a graph theory, as I hinted at the beginning. And okay, so we have been able to do this with a computer, and this is, of course, believable that you can simulate it on a computer because you have to list finitely many elements according to certain rules, and graph theory is one of the one of the best studied actually subjects in theoretical computer science. So it's not too surprising, but it required a certain amount of work. Anyway, this list has something like 3,000 elements. Now, once you have these 3,000 elements, you want to actually use, rather than simple Gauss-Bonnet considerations, more sophisticated considerations on spherical polygons and on spherical geometry to actually discard many of them. So there are quite a few pen and paper restrictions on the topology that you can write down. So we started doing them, and they became more and more complicated. So they're a lemma in spherical geometry, but with pen and paper, we can essentially prune the list to around 500 cases or so. But at a certain point, they become actually exceedingly hard. I mean, even when we were around the 500, to just get an improvement and get rid of 10 or 20 of them meant actually writing very long proofs in synthetic geometry. Okay, so that's where actually we started thinking about a way to implement a computer code which could actually look at these, 3,000 or 500 cases of whatever remained, and try to implement some smart inequalities, or iterate some smart inequalities in a way that actually could help discard the cases which are not realizable. So what we did is, remember that I told you that there's a lot of monotonicity considerations in Heppe's paper. We actually made some of these monotonicity considerations quantitative. Okay, this is one tool. And this is very useful for those faces of the, the link of this of the cone is, of course, identifying faces on the sphere. And many of these faces are actually convex polygons with angles of 120 degrees. Unfortunately, there are others which are polygons where the angles are not necessarily 120 degrees, and this is because there are these additional special points p and minus p. So on the convex faces, we can actually profit from the work of Heppes, from a quantification of these inequalities. But when we are actually looking at the non-convex faces, then we cannot profit anymore. On the other hand, one way to think about it is that you have this polygon where you know certain angles, and you want to know whether assigning certain edges to the polygons actually closes the polygon or not. And this is an interesting problem. It actually is a problem which can be described in purely algebraic terms, and it can be described in purely algebraic terms using quaternions. In fact, if you look at the cosines and sines of the length of the arcs in the geodesics net, which we want to describe, you discover through these algebraic conditions that they are determined by a system of polynomial equations with integer coefficients. So ultimately, this classification can be actually recast, given the topology, in finding all solutions for a system of polynomial equations. The problem is that there are really very high degree equations and many equations. And so the problem, if you want to actually go in this direction, is that the polynomials are too complicated to be able to solve, even with the modern software, which actually is extremely powerful, like using Gröbner bases and so on. However, if you are lucky enough in certain situations in which you are actually sweating to understand, for instance, using synthetic geometry, whether a net could be in this family or not, some of the things that you can actually deduce from the polynomial equations might help you a lot. Okay, now what actually happens is that the system is overdetermined. So if you just typically write down the number of unknowns and the number of equations, you discover that you have one more equation than unknowns. So solutions are rare, and pure algebraic solution of the problem, though, is unfeasible because the degree of the system is huge. But on the other hand, most of the times you're actually not expecting to find solution. This is the reason why, even though there are 3,000 candidates, topologically, only 30 of them are realizable. Okay, so by using this theory, we actually produce a computer algorithm that does the following. So as an input, it takes the topological graph. Then you can give to the computer a tolerance, delta bigger than 0. And then the computer actually outputs two possible answers. One answer is that there is no possible geodesic net with that topology. And the reason is that it actually proves you that even given the tolerance delta, there is no approximate geodesic net with that topology, which is satisfying what we're saying. So, and the approximation means that I allow the computer to be uncertain about the edge of the length of the edges. So to make an error of size delta in them. Of course, another possible output is that there might be a possible geodesic net. And then the algorithm predicts actually the length of its edges up to an error which is smaller than this delta. So this delta is somehow the error that I allow the computer to make in the precision of the length that it actually spits out. So the algorithm really guarantees you that if there is one such net, then the length of the edges is determined up to this error delta. Of course, the algorithm must be able to actually produce more than one candidate in the case in which there is more than one candidate. And that's the situation in which you might run into troubles. And like, if there is a one parameter family or two parameter families, the algorithm could actually take a huge amount of time to complete because delta is maybe a very small discretization parameter. So this, in fact, suggests that when you want to understand, multi or one of these examples in which there's more flexibility, you actually would like to solve that problem with pen and paper and not with the computer. And in fact, this is actually what happens. Now, the theory is still important to give you two things which are fundamental. So one thing that a computer is certainly for the computer is hard to process is a number which is very small but non-zero. So using the minimizing property that we have for the cones, we actually prove effective lower bounds for the length of the edges. And effective means that, of course, out of the theory, you could prove that, there's a lower bound by some constant, but we want this constant really to be something manageable, something like, 0.01, if you're looking at the net on the sphere of radius 1. Another important ingredient is an hard estimate on propagational errors when you are composing isometry. So one of the ways in which we actually try to see if a polygon can close itself, one of the polygons which is not convex, is by actually going or parallel transporting ourselves along the path and see if once we actually close the path, our isometry comes back to be the identity. But you see, of course, that I might actually run into problems of propagation of errors, because if I don't know the length of the edges, I make a little error on the length of the edges, then, of course, I might actually, while I'm making this tour, I might actually have a propagation of these errors, which means that maybe my estimate on how far the final isometry is from the identity is too coarse to actually allow me to conclude that that particular polygon is not feasible. So we need actually a hard estimate which is pretty sharp. And it's one of the places where we have actually to optimize if we want the running time, which is not too long. Anyway, so decode reduces the list of candidates to roughly 30. And as I said before, by pen and paper, we actually classify then some cases, especially the cases which are not rigid. Because the cases which are not rigid are then the ones which are like, hardest to kind of understand with the computer. In the remaining cases, actually, it happens that essentially all but 2 edges are determined, and decode gives the edge length of the determined ones. Now, in a couple of pen and paper cases, we also guess a certain symmetry, which we are not able to prove by elementary considerations in spherical geometry, and that is where actually we use this algebraic system of equations for cosines of the edge lengths, and then some hard computer-assisted algebra, I mean, like, some group-net basis, which is able actually to factorize the large polynomial. Okay, so now we actually got our, possible candidates. And for some of them, we have a very precise description because, the computer plus pen and paper consideration really gives a complete classification. But for the others, actually, we don't even really know that there is such a candidate. We only know that we can approximate it up to an error delta with our computer code. But we have a certain uncertainty. So we only know that maybe in the vicinity of a certain almost candidate, there is a candidate. Now, what we would like to do? Well, one thing which is very nice is actually that you could use Braque's surface evolver to produce competitor for the cones which are not listed in our theorem. So there's, of course, one subtlety, and it is that we do not exactly know the net because the computer classification of even the candidates is not exact. But if we know the net with sufficient precision, we can actually say that a competitor for the approximate net, which has a sufficiently large gain in area, would be able to gain even for every net which is sufficiently close to it. And so because actually the other part of the algorithm guarantees you that you are nearby in your candidate, you're able to beat this guy. Now there's a problem though. So Braque, in principle, if you actually feed to it a competitor which is admissible to Almgren condition, which tells you how to possibly modify the competitor, Braque's code is actually not supposed to change the topology, and so it should actually give you something which is compatible. The problem is that we know for a fact that the code does contain some bugs. They do not look serious because most of the times, actually, it gives you answers which are pretty reliable, but sometimes it gives answers which are actually strange. And that's probably because in the implementation, I mean, not in the conceptual part, there might be some little bugs. So, of course, at that point, Braque is not guaranteeing you that the competitor satisfies the boundary condition. However, Braque's output, once you actually let the code go and spit out a competitor which is kind of making better, is a piecewise linear immersion of a simplicial complex. And the computer actually gives you the piecewise linear immersion of the simplicial complex. So at that point, what we actually did is to devise an algorithm that takes the piecewise linear immersion of the simplicial complex and checks separately. And now it becomes a check on a simplicial complex. So it becomes a finite computation that the computer can perform very well. It checks whether it actually respects the boundary condition. And this is where we had to study somehow topology, because if you remember, Almgren's prescription is that you show the existence of certain maps. And so out of the piecewise linear data that we have for the simplicial complex, we have to kind of check, or we have to give conditions which guarantee the existence of the map. Okay, so this is what I just said. So we use consideration in low-dimensional topology, and okay, then we produce somehow the maps from Braque's data, and then after running the computer for all the cases that we cannot actually exclude by hand, we know that all but those 6 which I showed you actually survive as candidate minimizers. Let me also warn you that Braque actually sometimes gives you competitors which gain less than 1% in area compared to the cone. So there are actually some cones which are not minimizing, but which look very close to be minimizing. Okay, so just some acknowledgements. The research of this talk has been supported by the Simons Initiative on the Geometry of Flows, but you have seen that I had actually 3D models which I dipped in soapy waters, and in fact, they were extremely useful even to help us understand how to prove the theorem. And so these were actually printed by 2 engineers in the University of Passau, Michael Niedermayer and Dörte Rüweler, and probably without their help, we wouldn't have actually be able to complete the proof. And then we had several discussions with Guy David, Jonas Hirsch, and Simon and Steinbrüchel, which were of fundamental importance. I already hinted at the fact that there are many open problems which we cannot address, but since I'm actually going extra time, let me just not go into this and complete by saying happy birthday, Dion.
Well, great, Camilo, great talk. Thank you very much. Are there questions? Okay. Okay. Yeah.
Are you doing the coding, Camilo? Yes.
So I happen to be extremely lucky because Federico is a top performer even in the computer science Olympiads. I mean, in the computer science and math Olympiads. So no, I've not been doing the coding. So he's been doing most of the coding. I've actually been reviewing his code. We did discuss though the algorithmic part. But yeah, I mean, I wouldn't be able to, even do what Federico did for this project in probably 20 times as much time as he actually needed to do that. But I did actually look at a lot of the coding after it was produced and tested it myself.
Okay, good. Yeah.
Hello, Camilo. So among the cube geometry examples, do you expect any of them to be area minimizing mods on P?
Okay, with the boundary, okay, so, I didn't try. To tell you the truth, I didn't try. One thing that I had at a certain point as an idea is that if you put a group with, I mean, if you could prove that something is minimizing with a normed group where the norm of any element is equal to 1, then you would have actually an Angren minimizing set. But unfortunately, it seems that none of these examples is amenable to this. There are simple topological considerations. So I'm afraid actually the answer to your question is probably no, but I didn't check carefully.
Thanks.
Other questions? Yeah.
Hi, Camilo. Can you go back to your one of your example where the cone is over a cube? Like you mentioned, if the boundary passes through the midpoint of an opposite wedge, then it's not minimizing.
Yes, it's not.
Yeah, I'm a bit curious. What happens if you like slightly move the boundary, like from passing through the 2 vertices to the edge, and what happens?
Right. Okay. So the fact that when the point P is actually in the middle is not minimizing is because the competitor that Gene Taylor actually uses is good even for this. Because the competitor opens a little square in the middle. And if you open the square in the correct, you have, of course, 3 planes over which you can open the square. If you open the square on the correct plane, it will still contain that red line. So now, of course, out of stability, you would say, if I move the line a little bit away, I can just perturb my competitor a tiny bit and give you a competitor. And this you can do it theoretically. Now, the simulations with Brache actually seem to suggest that it still keeps being non-minimizing for quite some time. So you do have to get somewhat close to the vertices to actually believe that you maybe are minimizing. But definitely at a certain point, it seems, I mean, you get close to it, but not so close. But okay, if you try the simulations with the Skeleta, which I tried, the problem is that the square which is opened is very small. Actually, the film does try to open a square, really. But the square is very small, so the simulations are not that reliable, I would say. I mean, like, you know, the actual experiments. One would need an apparatus which is much more precise than what I was able to use.
So are there experimental examples where the boundary doesn't pass through the vertices but still like lies on the opposite edges of the cube, which is minimizing?
Sorry, say it again.
So I guess later in your experimental picture, you're showing the boundary pass through the two like opposite vertices of the cube.
Yes. Oh, yeah. I have run experiments even when you actually go through the edges. Yes.
Okay.
And when you pass through the edges, it seems to pick almost the Taylor's competitor. Of course, not exactly, because the Taylor competitor doesn't have the 120 degrees and so on, but it gets scarily close to it. It opens a tiny square in the origin, so it makes a little film which is a little square, and then tries to fit the other faces on this square. Yeah, that's what the experiment which I ran actually seems to show.
I see. Yeah, thank you.
Other questions from the audience? Okay, if not, thank you very much, Camilo. Great talk.
Very welcome. Thank
Good
you.
talk.
Thank you for the invitation. Happy birthday, Leon.
Oh, 15 minutes, I guess. 10 minutes.
10 minutes.
10 minutes, okay. with Gerhard Heusgen, who has been in the subject for more than 40 years. First time I met him was in San Diego, 1985, I think, in San Diego for a year. And Hamilton was there. We were working on rigid flow. And Hamilton was very excited to see how to compare rigid flow with mean curvature flow. So Gerhard started the mean curvature flow and did the important, fantastic work that Richard was very impressed by. So from then on, rigid flow is a pair with mean curvature flow. And Richard said that it has to be compared because there are many important features. Together, rigid flow can learn from mean curvature flow, and mean curvature flow can learn from rigid flow. So of course, a spectacular success of rigid flow in the last 20 years has been very important. And at the same time, mean curvature flow has achieved its great glorious. A lot of work was done by Gerhard and his friends, and with his many students, including Simon Brendel, and I think this will be very important to see his continuous development. And so he's going to talk about mean curvature flow swept out of asymptotic flat free manifolds.
Thank you, Yao, for the introduction. And I still remember how I first met Leon in 1982 in Heidelberg, when he gave the first time, I think, his lectures on geometric measure theory. And it was one of the luckiest breaks of my life that he invited me to Canberra that year. So in '83, not just did he invite me to Canberra, when I arrived, and I thought, I'm free now, he told me, oh, you have to present this interesting new paper that just appeared from a guy called Richard Hamilton. So it was lucky that he got me into geometric evolution equations at the time. And then he also introduced me to Yao in 1984, first time. And Yao introduced me to general relativity and taught me that geometric flows might play a role in general relativity. So today, I would like to give a lecture which also combines geometric flows in some sense with general relativity. And the setup, to see how this works. Okay. I'll go back. Yes, here's the setup. The general setup is we look at Riemannian target manifolds, and we have a smooth hypersurface. And my notation is going to be that A is the second fundamental form of the hypersurface, and I have the eigenvalues lambda 1 up to lambda n. The mean curvature is the sum of the eigenvalues. The outer unit normal is nu, and then the mean curvature vector will be direction of the direction of the flow. So mean curvature flow is a family of solutions. Let me give you some of the background again. A family of hypersurfaces such that the speed is exactly this mean curvature vector. That's a quasi-linear operator on the right-hand side. And with some initial data, it becomes a quasi-linear parabolic system. For smooth initial data, we get short-term smooth solutions, certainly. And it's the gradient flow of the area, functional. And very importantly, when you then try to understand the geometry of the flow, you have to compute the time evolution of the geometry, meaning you have to compute the time evolution of the second fundamental form. And it turns out that that turns into a reaction diffusion system where the most important term on the right-hand side, apart from the Laplacian, is this cubic term, second fundamental form squared times second fundamental form. But if you're in a Riemannian manifold, you have some lower order terms that become important in applications. So we have some product terms of second fundamental form and Riemann tensor of the ambient manifold. And you even have some terms involving the gradient of the Riemann tensor in the ambient manifold. The mean curvature itself satisfies the Jacobi equation, the Jacobi operator on the right-hand side, the operator that is familiar from the second variation formula of area. Now, the quasi-linear system of mean curvature flow for short time has similar smoothing properties like the ordinary heat equation. So you get a very nice estimate for higher derivatives of curvature, even if you started only with bounded curvature. So you get exactly the kind of estimates that you expect from the ordinary heat equation. And this regularity theory can be further refined. You can make it into local estimates for the curvature. So you can localize this estimate in space, and you can refine it in Hölder spaces if the initial data are in some more complicated Hölder space. So you have sort of a very nice natural scaling invariant local theory that allows you to rescale singularities and blow up solutions in a parabolic setting. Now, in this lecture, I want to concentrate on a very special case. Just look at two-dimensional embedded hypersurfaces of positive mean curvature in a smooth Riemannian manifold. And these two properties, embeddedness and positive mean curvature, are both preserved under mean curvature flow, as we saw in the equation for the mean curvature. For example, ddt of h is the Jacobi operator acting on h. So definitely positive mean curvature is preserved. We stay in this class, and that greatly restricts the long-term behavior, the singularities that can occur under this flow. So, for example, the embedded self-similar solutions that play an important role for positive mean curvature are the shrinking sphere, the shrinking cylinder, and then there's also the embedded engined torus, which of course does not have positive mean curvature. But these are important solutions that are self-similar shrinking solutions of the flow. The general singularities are more complicated. In Euclidean space, for example, you can show that the convex surfaces contract nicely to a round sphere. So when you rescale this, you will see the self-similar shrinking sphere that I had on the previous picture. But then if you drop convexity, then the singularities can be more complicated. In particular, you can have this neck pinch that you have to have such singularity. It can be easily seen by creating an initial surface that looks like a dumbbell, where you put the two spheres very large in the two balls at the end of the dumbbell. And then you make the neck so small that you can put a small engined self-similar torus around it. And then if you arrange it, it's clear that the engined torus will die before the two spheres die. And since we have this avoidance principle between solutions of mean curvature flow, there has to be some singularity in the middle before the two pieces at the end have a chance to come in. Now, it turns out, just like in Ricci flow, and Yao mentioned that mean curvature flow has so many similarities with Ricci flow, just like in Ricci flow in 3 dimensions, you can have also a more nasty singularity, more difficult to analyze singularity that has a different blow-up rate than the neck pinching that I showed you on the previous picture. So you can have this situation, non-generic situation, where sort of the right bubble has just the right size compared to the left bubble in the dumbbell picture, such that it doesn't quite make it through, and on the other hand, you don't get a nice neck pinch either, so it gets stuck, and then when you rescale at the tip, you see a translating solution rather than a self-similar shrinking solution. And it is a long horn like I try to draw there. Now, the idea is that if these are the only singularities that can happen, that the flow can be extended past singularities, just like we can extend in Paramount Hamilton's work, the Ricci flow past singularities, namely when you develop a long neck, that you can then do surgery at the end of these neck regions, and you can do the same thing with just one spherical cap being introduced if you have one of these singularities that look like a horn. Now, this has to be done carefully in a quantitative way, just like in Ricci flow, and there's a certain scale involved, right? So you have a radius where you have the highest curvature in the neck, and you have then a radius where you do the surgery, which is going to be much bigger. So there will be, you want to heal the surface, you want to reduce the curvature by a fixed factor 1,000 or so. So you have to do this very carefully, but you have still a certain freedom in the parameters because you could wait longer, so you could wait until the curvature is bigger, so you could make this scale smaller where you do the surgery, as long as you keep the ratio between the curvature where you stop the flow and do the surgery and the radius where you introduce the hemisphere fixed. So you want to keep this factor 1,000 or so fixed, but you can then let the scale of the surgery actually tend to 0. The price you pay for that is that you have to do more and more surgeries. Now, to sum up, what happens in the two-dimensional case is the following theorem that I proved together with Simon Brendle in 2016 in Euclidean space and 2018 in the general Riemannian setting. So you can start with any hypersurface of positive mean curvature that is embedded in any three-manifold, no assumption on the curvature of the Riemannian three-manifold. And then you have only 2 possibilities. You either you have these singularities, you have to do these surgeries, and then the only thing that can happen in the surgery, as I draw through the picture, is that you do the inverse of a connected sum. So you might develop more connected components of the surface, and these connected components either contract to round points in finite time. There's a non-generic possibility that they contract to a curve in finite time. For example, if you're in Euclidean space, you take a symmetric thin torus and let it evolve, it will converge to an S1. Or if the solution does not develop any singularity for some of the components, then they will exist forever. And because they are always decreasing area, the only chance that they don't become singular is that they converge to a minimal surface. And the surface of the genus of the surface, because we are only doing this cutting of necks, has to be less or equal than the genus of the initial surface. And an important point is that we can prove that this will happen in a smooth way. So there will be a certain time from when onwards, there will be no surgeries necessary anymore. So this convergence in the end will be smooth, and because you then approximate this limiting surface by a family of non-negative mean curvature surfaces, this limiting minimal surface will also be weakly stable. And another consequence of this is if you start with a sphere, then you might have many surgeries, so you might end up with many connected components, but these connected components then will all be spheres. So the second possibility, if you start with an S2, the second possibility can never happen. Now, what does this have to do with, yeah, let me first draw a picture. So what can happen? So in pictures, I told you the round point limit can happen. The shrinking tube can happen, but it cannot happen if you started with an S2. You can have a complete smoothness, all right? So in the limit, in this picture, t tending to infinity, the solution converges to a nice smooth minimal surface. You could have the thing breaking up and then converge to two minimal surfaces, as in this picture. Or it could be that the surface breaks up into two pieces, but then in the end, for t tending to infinity, these two pieces might then approach from the same minimal surface, but from different sides inside the three manifold. And this lines up also with work of Brian White, where he showed that under mean curvature flow, which he considered from a level set point of view, you can never have three solutions, three embedded solutions more than three embedded solutions come together here. So this would be here the example where you have two dynamic solutions of mean curvature flow and one static solution of mean curvature flow coming together. Now, let's sum this up. I told you about this parameter of surgery that you can let tend to zero. So if you do that, a former student of mine, Joan Head, and independently Joe Lauer, proved that if you let this parameter tend to zero, then you recover the level set flow that was initially introduced by Chen, Giga, Goto, and also by Evans Sprague. And that was analyzed in terms of its regularity in great detail by Brian White. So the surgery solution and the level set solution fit together if you let the surgery parameter tend to zero. And in fact, we used some of the arguments of Brian White to show that the surgery solution also is smooth for arbitrary large times. Now, let's see, how can we apply this to general relativity? Three manifolds in general relativity appear as as space-like slices in a Lorentzian four-manifold. For example, if it is a star, then the slice you should imagine like the lower picture, where around the sun, you have some matter, and then you have sort of this well inside the three manifold, or you have a black hole, like in the Schwarzschild solution, and then you have a three manifold that looks like a catenoid. Now, what I'm interested in is the exterior region of this three manifold. So I'm looking at the outermost region outside of the largest black hole. And to put this mathematically, we're going to look at a three manifold that is diffeomorphic to R3 outside a finite number of balls. And we have then a boundary, possibly, maybe there's no ball being cut out, and there's no horizon. But if we have finitely many horizons, in the simplest setting, we assume that the mean curvature of these horizons is zero. So in general, to simulate to model all the important phenomena. But on the other hand, it has to be strict enough that you can prove something about invariants that are of physics interest, like the mass, center of mass, momentum, and so on. So if you want to talk about mass, then the decay conditions that I wrote down there are just the right ones with some positive epsilon. And from physics considerations, dominant energy theorem, and so on, you can deduce that in this situation, we should make the requirement of non-negative scalar curvature of the three manifold. And under these conditions, the mass introduced by Arnovit, Deser, Miesner, ADM mass, is well defined, and the famous positive mass theorem by Shen and Yao asserts that it is non-negative with equality if and only we are in a Euclidean 3 space.
Defined by Einstein, almost in the second paper.
Yeah, there was a long sequence of ideas. Einstein and then Hermann Weyl also had
But
related
this
to.
one is already. Yeah.
Yeah, okay. Okay, so now how can we make use of the result that I obtained with Brendle or with the level set flow that Brian White studied? So the idea is now to take such asymptotically flat 3-manifold that has some regions of positive scalar curvature, some horizons. Well, we want to start with a very large surface that will satisfy our conditions, of course. It will be diffeomorphic to a sphere. It will have positive mean curvature. It's embedded. So the theorem that I wrote down with Simon Brendle applies. You can start from a huge coordinate sphere and move it into the interior. And then what can happen is that we have some surgery, that then one connected component contracts, say at the center of the star at the left, and the other component converges to the minimal surface at the boundary of the black hole. And if we are really in an exterior region, so there is no other minimal surfaces except these boundaries of black holes, then we get a complete sweep out between our initial surface, which might be a large coordinate sphere near infinity, and all the way down to the boundary of the black hole. Now, it's very interesting in order to study other things like center of mass, one would like to have a foliation not just inside such a compact region, inside a large coordinate sphere. One would like to have a foliation all the way to infinity. And that was studied in particular by Xingdong Yang and myself in the 90s when we proved that there is a constant mean curvature foliation far away. We had to assume much stronger decay conditions at the time, but then with the work of other people, Metzger, Christoph Nerz, Carla Zederbaum, the existence of constant mean curvature foliations near infinity that provide a concept of center of mass was established under exactly those decay conditions that I wrote down, or roughly these decay conditions. I'll say a bit more about this later. So we want to extend this all the way to infinity, not just up to some even large coordinate sphere. We want to really have a foliation all the way from infinity up to the horizon. Now, for that, I have to tell you about a different theorem, namely the rigidity of mean curvature flow at infinity that I established with Carlo Sinestrari in the case of Euclidean space. So we want a solution that comes from infinity. That means we want to find an ancient solution, a solution that starts at time minus infinity and then exists all the way. And in Euclidean space, it turns out that if you only look at surfaces that are uniformly convex, so if you look only at solutions of mean curvature flow such that for some fixed epsilon, that's the same epsilon for all time, on each surface, all the principal curvatures are comparable to the mean curvature, so at least epsilon times the mean curvature, then the only solution that exists for all time backwards to minus infinity are the shrinking spheres. So the shrinking spheres are rigid in the class of ancient solutions that are uniformly convex. And the proof idea there goes back to some work I did in 1984 when I was in Canberra with Leon. And the key point is to look at the trace-free part of the second fundamental form. And then you try to make it scaling invariant, and you take the trace-free part squared and divide it by the mean curvature squared, but not quite. You divide it by a little bit less than h squared. So you break the scaling invariance by a small power of the mean curvature. And then it turns out, using the Kodazzi equation, I learned how to use the Kodazzi equations for this purpose. I learned it from Leon, from his lectures on minimal surfaces. And you get inequalities, and you use Simon's identity, and you use Sobolev inequality of Michael Simon. And then you end up, after the long computations, you end up with an evolution equation for LP norms of this F sigma, where you have a negative term on the right-hand side with a higher power of the same quantity. And since you have also control due to the uniform convexity on the development of area, that's the last factor in this inequality on the right-hand side, you can see that it is not possible to have a solution to this inequality on an infinite time interval back in time. And this can only mean that already the trace-free part of the second fundamental form is identically zero, giving you the result that the surfaces must have been completely round. And it's of course well known that you need some uniform convexity condition, because Brian White constructed solutions that look like a football and are ancient solutions. They are like two translating solutions of mean curvature flow, two balls on a collision course. And for large negative times, it looks like an American football. So the convexity condition is necessary and gives you this rigidity. So it's rigid, of course, up to translation in R3. You could center this family of concentric spheres anywhere in R3. But we know that the positive mass theorem, in the case of non-trivial three-manifolds, asymptotically flat three-manifolds, removes the translation invariance. If we have a asymptotically flat three-manifold with positive mass, the whole point of foliation that I explained is that the positivity of the mass removes the translation invariance near infinity. So the hope would now be that we can combine this method with the theorem of Simon-Brandle to construct a unique solution of mean curvature flow coming from infinity, where also the translation invariance is removed. So here's the idea: transfer the rigidity estimate for ancient solutions to the asymptotically flat setting, remove the translation freedom in the special case of positive mass. And it turns out to construct such a solution, we need a slightly more stringent condition on the asymptotic fall-off. We need some symmetry condition on the metric, some antipodal symmetry on the metric and the connection near infinity, which also turns up in the proof of existence of a foliation of constant mean curvature under these weak asymptotic conditions near infinity. So it's the same condition that you need to control the position of CMC surfaces near infinity. So we employ this condition also now on our three-manifold studying mean curvature flow. And what we can prove in our first theorem is that if you have an asymptotically flat region satisfying the decay conditions I wrote down first, and if you have, in addition, the weak Regge-Teitelbaum conditions that I just wrote down, then if you have the non-trivial settings, you have positive mass, then you can actually construct an ancient solution, sigma of t, all the way back of mean curvature flow, which is uniformly convex near infinity. In fact, you can make the constant 1/4, you can make it as close to 1/2 as you like. So it's uniformly convex near infinity. And we get for our solution sharp a priori estimates as similar as in the constant mean curvature setting. So in the constant mean curvature setting, you would have also the trace-free part of the second fundamental form squared less than a constant time over r cubed plus 2 epsilon. Now, in our case, we don't have the luxury of constant mean curvature, so we also have to estimate the mean curvature, how close it is to being constant. So we have this estimate of the mean curvature compared to the average of the mean curvature, which I denote by little h, and we get an estimate of the mean curvature squared. Now, these are the key a priori estimates, and I'd say something about the proof later. Our second theorem, which is we are quite certain of, but it's not yet written down completely. We are still checking everything. Theorem A is finished. Theorem B, we hope to finish in the next month or so. So that's the uniqueness. So now we want to prove that this foliation is actually unique. And just like in the case of constant mean curvature foliation, where if you want to show that the center of mass actually exists and is unique, you need some slightly stronger, you need the strong Regge-Teitel-bound conditions, which I didn't write down, but it means you also assume some symmetry of the Ricci tensor on the scalar curvature with the appropriate decay. So they're slightly stronger than the weak conditions, and that ensures the uniqueness of the center of mass given by the constant mean curvature foliation. And I think it's exactly the right condition that we also need to prove that we have a unique solution of mean curvature flow in the class of surfaces where the radius mod x of the surface is comparable to the area radius of the surface, and in the class of surfaces that are uniformly convex for some sufficiently negative time. So that's the ultimate goal, and I think that's the ultimate theorem that we're going to have, that we not just have existence, we have a unique solution in this class, and it will satisfy the a priori estimates that I had on the previous slide. A few words on the proof. The surfaces and the properties. I think it's a nice foliation because we get a center of mass again, consistent with the previous center of mass. And we will have a foliation where the Hawking mass is always bounded by the ADM mass. We want this property to be true. And it is a foliation which is particularly nicely adopted to the isoperimetric profile near infinity. So phi is the isoperimetric profile of a Schwarzschild solution that assigns to a given area of a concentric sphere in Schwarzschild the enclosed volume with respect to the horizon of that sphere. And if you compare that isoperimetric profile to the development of the volume under this mean curvature flow, then it is exactly the same if you get 0 on the right-hand side if you are inside Schwarzschild, and otherwise you get this monotonicity which allows you to read off the mass actually as an isoperimetric defect at infinity. You just have to look how far you are, how much more volume you can put in a given surface area in order to read off the mass, which is a more geometric way of looking at the mass than the coordinate-dependent formula that we saw in one of the previous slices. So I think in this sense, the mean curvature flow solution really provides a nice sweep out, a unique sweep out of the three manifold all the way from infinity to the horizon. The level sets are sort of a replacement of the level sets of the Newton potential. And here's some of the names involved with the CMC foliations. And we also drew in our analysis on recent work of a PhD student of Carlos in Distrari, Jacopo Tenan. Few words on the estimates. So we take this estimate that I had on the board in Euclidean space, And then if you do this in the asymptotically flat setting, you get some error terms involving the Ricci curvature. And you have to do a lot of work, Sobolev inequality, Moser iteration. In the end, you get from this inequality up there, you get a sub-estimate on the trace-free part of the second fundamental form. And another important step, however, is you have to get the gradient estimate on the mean curvature, because that's the thing that's really different from the CMC surfaces. And the key idea there is that when you look at the evolution of the trace-free part of the second fundamental form, you get this Bochner term on the right-hand side, which is better than it looks like. By this Kato inequality in the Kodazzi equations, you get more out of the gradient, out of this term, this first term on the right-hand side. You have left something over. And that is, again, that goes back to something I learned from Leon in 1984. So this idea how to exploit the Kodazzi inequality has a long history, and you can then combine this trace-free part with the gradient term in order to cancel the bad terms that you get from the gradient evolution of the gradient of the mean curvature, and you can use your already established estimate on the trace-free part of the second fundamental form to get the gradient of mean curvature bound. That is crucial. You have to still do a lot of work to make it interior in time and so on, but these are some of the crucial ideas. And this is now giving you the roundness, and once you have the roundness, you can control the spectrum, you can control the Jacobi operator, and you exploit finally the positivity of the mass to see that the surfaces cannot shift away, and that is finally giving you the uniqueness. This is where the positive of mass comes in after you establish that your surfaces are beautifully round. And that ends my lecture, and best to Leon's side.
Okay, thank you, Gerhard. That's a great talk. So let's see, questions from the audience? Yeah.
Can we give the lower bound of the genius of the third case in Brandel's theorem in slides 10, slides of 10?
You mean a lower bound on the number of surgeries that we have to do? Is that the question?
No, the number of the linear hypersurface genius.
I'm not sure about the question. I think in general, this inequality I wrote down, that the genus of the final configuration has to be less than the initial one, is the best you can do, unless you make extra assumptions about the initial data and the three manifold.
Okay, next.
Thanks for the nice talk. I have a question. What is the physical interpretation of the mean curvature foliation? And related to this, is there any relationship between the time coordinate when you write down the mean curvature flow and the Lorentzian coordinate for time?
Well, there is no relation between the physical time, and this is just a parameter. It provides, in some sense, the time of mean curvature flow. In some sense, provides a natural radial, a geometric radial coordinate in the asymptotically flat three manifold. And you ask, what is the physical interpretation? Well, the point is that this flow, this mean curvature flow, now incorporates some of the key structures that are of interest physically. It incorporates the horizon, it finds the horizon. And I know from my time at the Max Planck Institute for Gravitational Physics, talking to the physicists, they are actually using mean curvature flow to find the horizon, because for them, it's an important problem when they do the evolution of Einstein equations and they go with these three-dimensional slices through time, and they have two black holes on a collision course. Then at some stage, around the two horizons, there will be a new horizon forming for the joint object. And they have to catch that moment. So they have to know where is this new horizon in order to make the numerics stable. So they actually, in some of their algorithms, they use mean curvature flow to find the outermost horizon. And they can do this even in the space-time setting, which I only concentrated on the time symmetric setting here. And the other thing, it incorporates, as I said, the mass, because you can read it off from the isoperimetric behavior of the foliation. And it incorporates the center of mass, because it has sort of this unique limit near infinity. So it incorporates the three most important structures that you can incorporate in a three-dimensional slice without taking into account the second fundamental form with respect to the form manifold.
Thank you.
Okay, one last question.
So from the work in progress, can we derive a new proof of the Penrose inequality?
I don't see how I can get a new proof of Penrose inequality out of mean curvature flow. It's more the other way around, that I can use inverse mean curvature flow to control the properties of mean curvature flow. For example, the fact that all these surfaces of mean curvature flow are outward minimizing means I can then use them as a starting surface for inverse mean curvature flow, and the Garrosh monotonicity formula will hold along them. And that, for example, gives me the inequality that the Hawking mass of all my level sets has to be less than the ADM mass near infinity. So I can combine mean curvature flow and inverse mean curvature flow. So inverse mean curvature is telling me something about mean curvature flow, but I don't think I get out of mean curvature flow a new proof of the Penrose inequality. At least I didn't see it. Maybe, it would be great if.
Okay, great. Thank you very much. Gerhard, nice talk. And let's go to lunch. Thank you.
happy to have Professor Wickramasinghe and Professor Krumer give the first joint talk. The title of their talk is Analysis of Singularities of Area Minimizing Currents, a New Framework. Let's welcome.
Thank you for the introduction. Can you all hear me okay?
Yes, we can hear you.
Okay, great. And yeah, thanks to the organizers for inviting me to give a lecture here at this conference. So my talk is the first part of a two-part presentation on joint work with Brian Crummell. Brian will take over right after me for the second half. I really wish I could have been there in person for this this very special event celebrating Leon and his work, and also more broadly work in geometric analysis in the past 50 years. I had intended to be there, but when at the last minute, I had to change my plans, unfortunately. I am, however, very grateful for the opportunity to speak, at least remotely, and participate in some small way in this event. This is very especially significant for me and Brian. I think I can speak for both of us here, because we were both Leon's PhD students at different times, and with me being the older guy, I guess, and the old guy. So our talk will be on a subject, regularity of high codimension area minimizing currents, whose origin goes back almost to the kind of the start of this 50-year period we are celebrating to the monumental 1983 work of Almgren. Our take on this problem, and again, I think I can speak for both myself and Brian here, has been shaped quite directly from Leon's work. And more broadly, we have benefited from the idea of bringing PDE theoretic thinking to geometry, something I learned way back when I was a student through the work of three of the main architects of that philosophy, Shane, Simon, and Yao. Maybe they're all in the audience. I'm not sure. I can't tell. Anyway, so before I get to mathematics, let me say on a personal note that I am very grateful to you, Leon, for your wonderful, inspiring, and encouraging mentorship all those years ago, and for your friendship and wisdom on many occasions since then. And also for introducing my brilliant collaborator, Brian, to me. That happened, you may remember, when you visited Cambridge on a sabbatical, and when Brian came with you, who was a finishing student at the time. And then Brian ended up spending some time after that, couple of years here in Cambridge after finishing a PhD. And that's when we started working together and did our first initial work, which eventually evolved into the results that we are going to present today. Right, so with that, let me just move to mathematics. I'm going to begin with the theorem of Almgren, which goes back to 1983, and it says that if you have an area minimizing n-dimensional current T, rectifiable current, then the singular set of that current has a dimension, Hausdorff dimension at most n-2. So this is in arbitrary codimension, and we are in Rn plus m for this talk and for the next one as well. But you could extend these things without too much difficulty to Riemannian manifolds, everything I said. So here, sing T means the interior singular set. So these are the points on the support of the current away from the boundary near which the support is not smoothly embedded. It's a usual definition of singular points, non-embedded points. Almgren introduced a number of influential ideas in this work, and almost immediately people absorbed that and used that in different contexts, in PDE and geometric measure theory both. But the proof in its entirety remained a sort of a typewritten 1700-page manuscript for nearly 20 years, something of a black box. And then Taylor and Sheffer in year 2000 transcribed this proof into a 900-page book after Almgren's death. And then Deleuze and Spadaro around 2015 took on the massive task of deciphering this work and streamlining and giving a proof in a modular, accessible form as a series of papers, following the same conceptual steps as Almgren, but significantly improving the technical clarity of the work. And this revitalized the work, the Almgren's work, after many decades of relative inactivity. So that's kind of the history of this theorem, and the bound is sharp, n-2 bound is optimal, and that's easily seen by algebraic varieties, these examples of algebraic varieties. So for example, I've written down two here. If you look at this example T1, which is the curve z squared equals w cubed in C2, as a two-dimensional object in R4, this is area minimizing for compact regions, has an isolated singularity at the origin. And the second example is wz equals 0, a pair of planes, orthogonal planes meeting at a point. Again, an isolated singularity for a two-dimensional area minimizer there. Notice that these are two different kinds of singularities. First one is if you take a tangent cone, then you, as a current, you get a multiplicity 2 plane. So it's a degenerate singularity. You lose information about the singularities once you pass to the tangent cone. And the second one is, it itself is a cone, and it's different. It's a multiplicity 1 planes crossing orthogonally. So let's just agree that, so we need to make this distinction. Throughout this talk and the next, understanding branch points is really the difficult part of this whole program. So the branch point, let's just agree that the branch point means that any singular point, you can always take tangent cones, that's just a general fact. We have area minimizing property that allows you to take as currents tangent cones, they're non-trivial. And let's agree that the branch points are the points where you get at least one planar tangent cone. I have to say at least one because uniqueness is a major issue as well. I will address all of these things as I go along. Uniqueness of the plane is a priori very much unknown. Okay, so with that, let me first quickly summarize codimension 1 theory. So most of these talks will be about higher codimension. But codimension 1 theory is very rich. It goes even back a decade earlier than Almgren's work. It goes back to the work of Di Giorgi, which implied that there are no branch points in codimension 1. So that's a very good place to start with in terms of analyzing singularities. You rule out branch points by proving that planar points are regular. That's true. And then you can go all the way down to codimension 7. So the sharp bound there is the Hausdorff dimension of the singular set is n-7. And this is a combined work of many people, Federer, Fleming, Di Giorgi, Almgren, and Jim Simons in the end. And then the next major breakthrough came in the mid-90s of Leon's work, which showed that the singular set actually has structure. This is a turning point in the subject in geometric measure theory, because it's the first time that it tells you that there is actually more structure than just the dimensions for the singular set. There's a major difference in our knowledge about singular points. So it's n-minus rectifiable, and not only that, Leon's methods gave the uniqueness of the tangent cone along the singular locus at almost every point. And this more recently, Neba and Valtorta gave a different proof, completely different argument that is very general, and also it covered Neba-Valtorta methods, gave us rectifiability, different proof, as well as including the finiteness of measure locally. Leon's method didn't quite reach that conclusion. So then, so that's on the side of the conclusions, but these are sharp, as I said, in 7 dimensions, you do get singular examples. But on the side of the hypothesis, it turns out that that can be weakened quite significantly. You don't need area minimizing when you're in codimension 1. What's needed is stationarity as a waterfall, so you don't even need a current structure in codimension 1. So stationary waterfalls with stable regular set and no classical singularities. So by a classical singularity, I mean sheets, smooth sheets coming together along a common n-1 dimensional boundary. For example, like a triple junction, if you have 3 half planes meeting along an axis, 120 degrees, that's an example of a classical singularity and or pair of planes. Once you rule out this very specific structure, very particular type of singularities, and if you're in codimension 1, if the regular set is stable, then you get all the previous conclusions I said about it for area minimizers. Notice that the area minimizing thing is subsumed by this condition, right? Because the classical singularities are not minimizing if you had a current sort of picture. So that's just sort of brings it in the umbrella of one set of hypotheses giving these conclusions. And that's that version that I said about getting the dimension bound is my work in 2014, which was based on the fundamental work of Shane and Simon in 1981, and then Shane, Simon, Yao in 1975. Again, early part of this 50-year period, this major developments that influenced the work that I did and also many other people. And then the rectifiability conclusion is more recent. It's by IX, McCurdy, and Minter for this class of stable hypersurfaces. And this theory continues to be developed further, actually, substantially. Most recently, it's Bellatini's exciting work, breakthrough work that extends Shane-Simon and Shane-Simon-Yao theories to the immerse case and providing curvature estimates under smallness of the singular set, non-immerse part of the surface. And then based on Bellatini's work, Holly Wang at first, and then finally Minter and my current student, Justin Xiao, who might actually be in the audience, I'm not sure, but I know he's back in China writing his thesis. They have extended this to the compactness theory for stable immersions in any dimension hypersurfaces, assuming the sharp conditions to rule out branch points. So, and in all these works, one thing you should, at this point, kind of remember is that the starting point is proving an estimate at planar points. When you have a tangent cone that's a plane, you want to prove a decay estimate. And that is the George's work to begin with for the area minimizing case, and it extends to Shane-Simon, my work, and all this works in the immerse case. Proving uniqueness of the tangent plane is sort of the starting point. Okay, we are going to transport that philosophy to the higher codimension, and that's the strategy we're going to follow. And I'll explain that in a minute. So another case we understand where we're now back to area minimizing currents of arbitrary codimension bigger than or equal to 2 from now on. And then another case we understand very well is the two-dimensional theory. So if the dimension is 2, then singular points are isolated. And then not only that, there's a complete structure theory around a singular point. The current is irreducible. If it is irreducible, then it is a branch point with topologically a disk. So the topological type is trivial. It's homeomorphic to a disk, and it admits a parameterization of class C3 alpha. And then moreover, there is an explicit asymptotic description one can write down, and that's the work of Micallef and White. You can apply Micallef-White theory to that setting. So these works go back to White, Chang, and then as I said, Micallef-White And then Delelis, Spadaro, and Spola revisited this theory more recently and clarified some parts of Chang's work, and I think extended it to a certain almost minimizing setting. So that's the story in 2 dimensions. But then in higher dimensions, if you're at a branch point, what topology is not so surprising, I guess, but can be non-trivial. And I've written down an example. This is an example that you should keep in mind throughout these 2 talks. That's quite relevant to what we are going to say in the end. And this example, again, you don't worry about kind of remembering what the formula says, but let's look at the features of this. It's an algebraic example, so it's area minimizing. So z squared equals w cubed times w squared minus u cubed. This is now, okay, so what dimension? This is 4-dimensional in R6, okay, as real objects. Area minimizing for its boundary for any compact region. And then if you look at the singular set, it's very simple. It's just a 2-dimensional plane. The U plane, okay? So 0, A0 for any complex C. So that's the singular set, and every singular point is a branch point of multiplicity 2, simplest kind of branching you can get, density 2. And then the tangent plane is the same everywhere, Z equals 0. These are all, you can compute these things easily. So that's a fixed tangent plane, and branch points at 2. So it's a full set of branch points, full measure. Not only that, it's actually just a plane, right? 2-dimensional plane. And then as you approach, so along this branch set, this singular set, if you look at the rate of decay to the tangent plane, at the origin it's 5 halves. So the distance to 5 halves power, because w to the 5th power, that's the dominant part. That's the other part, w cubed times u cubed is a low order term, right? That just drops out. And so that's coming in at rate 5 halves, but away from that, any point is 3 halves, okay? So there is a jump of the rate of decay as you come in this planar decay, planar frequency, we will call it planar frequency later. So that jumps. And on the other hand, if you can compute this, and I hope we did the calculation correctly, the fundamental group of this in a small punctured disk is non-trivial. And that means that it's not topologically a 4-dimensional disk, okay? You can write down examples, tons of examples like this, isolated singlets and all kinds of things. And then this is particularly relevant for us. And so this jump, so we will have a theorem later. So our interest is in understanding to what extent can you extend the 2-dimensional theory, right, to higher dimensions. In the simplest question you can ask is, are there some good conditions you can give so that the conclusion is that the thing is topologically a disk near the branch point. And it turns out that our theorem, we will have a theorem later on that says that exactly if this jump didn't happen of the planar frequency, then it is topologically a disk. So if you have enough branch points and they are all, if the frequency didn't jump at the point, then that rules out complicated topology. Okay. Hopefully we'll get to that, but I know I have to worry about the time. Great. So that said, so like I said, this is a program which aims to sort of understand kind of the structure. So we kind of switch from dimension bounds and structure of the singular set to kind of understanding how the current behaves as you come into singularity. This is kind of the broad kind of theme of our work. And it provides a conceptual shift from Armgren's work. We'll make a comparison. So I think it's helpful probably to the audience, rather than assuming that you are familiar with Armgren's work, just for me to give you a very broad overview of how the Armgren program works and then make a bit of a comparison. Kind of my sort of first goal of this in this talk, and then I'll hopefully have time to at least mention some initial results we get, and then Brian will take over and explain all the asymptotics and all the kind of the rest of the work. So Armgren's idea is sort of you take the singular points, that's for the branch set, script S arm for non-branch points. Okay. And then the first step is to what Amgren does is that the non-branch set is very easy to bound the dimension of. Because if we take a tangent cone, by definition, it is not a plane, therefore, and it can't have an n-1 dimensional spine, translation invariance, because it's area minimizing. So n-2 is the top order spine you can get, top dimensional spine. And based on that and a certain persistence of singularities principle, general fact about if you have the right type of dense singularities, they all accumulate along a n-2 dimensional subspace when you rescale. Based on that general principle, Amgren gives a very sort of elementary argument. This is Amgren's argument. This particular type of dimension reduction to show that the dimension of this S arm part, this S non-branch point set is n-2. Now that out of the way, then you look at the branch set, and that's by far the most difficult part because you lose this persistence of singularities, right? You have to look beyond taking tangent cones. No matter how you do this, whatever method you come up with, you need to do something beyond just taking tangent cones. That's inherent, the difficulty. And now we can say this in hindsight. Actually, another reason for the complexity of the classical theory is, in fact, is the sole focus is on the dimension of the singular set, which meant that one has to treat all branch points equally. So if you accept that premise, then I think complications are unavoidable. It does. That's kind of my take anyway. But if you incorporate the uniqueness of the tangent plane question to this, then you can find a way to simplify this. It's kind of counterintuitive. You're trying to do two things, but when you try to do two things, sometimes things become clearer. Anyway, so that's our way of proceeding, as I will explain soon. And then another distinction I want to make at this point is that this split of branch points versus non-branch points is a very qualitative split, right? There are no a priori, no estimates along any of these parts to begin with. And I will show later on, our techniques will first lead to a decomposition which comes with estimates built into it. And so then from there you can start to analyze the dimension and the structure and everything. So we will give a different quantitative division into two pieces. So as I said, uniqueness question was not addressed in the classical theory, but okay, what good is it? How is it going to help? Remember, in co-dimensional, I said that that's somehow starting point, right? So you prove uniqueness. Not only that, then you conclude that the point where the unique tangent plane exists is actually a regular point, right? You can do this in a whole neighborhood. Well, we don't have the luxury of that conclusion here because we know there are branch points, they do exist. Nonetheless, suppose you had a uniqueness estimate, okay, for a minute. It's a big assumption at this point. So what good is it going to do? Well, so if you had an estimate of this kind, the top here in blue, can you are you able to see the cursor that as I moved here? I hope you are.
Yes, we can see that.
Thank you. So in this estimate at the top here, so as you rescale the current, I'm assuming that it converges at a polynomial rate, right? So rate 2 times 1 plus alpha here. If this rate is quadratic, that means if alpha is bigger than or equal to 1, then what can happen is that the difference of the sheet. So imagine the current being like two-sheeted, right? Of course, the notion of sheets doesn't exist. This is part of the problem, right? It's not a PDE question yet. It just topologically could be very complicated. But assuming nonetheless that there are sheets, and there are approximate sheets actually, because it's very flat, what can happen is that the separation between the sheets can be going to zero faster than the current is approaching the tangent plane. So we are assuming that it's approaching the tangent plane quadratically. And let's say it's exactly quadratic. So in this example, like this, so look at this example. Z minus W squared equals W to the 5th. So that's the same as Z equals W squared plus or minus W to 5 halves. So those are your sheets, right? This is a two-valued graph. And the current approaches quadratically exactly to the tangent plane because 5 halves is a low order term that drops out. But then the separation, if I subtract these two values, you get W to 5 halves. So that's going faster to 0. See, when that happens, any attempt to get some information by blowing up relative to the tangent plane, remember, taking tangent planes is no good. We had a branch point. We lost the singularity information. Well, next step is, okay, let's suppose you have a tangent plane. Somehow, let's assume it's unique, as we're doing here. Then I do some kind of rescaling where you try to rescale more in the vertical direction and get some information. That fails as well, right? Because you get Z equals W squared when you do that. This drops out and you get a classical harmonic function. Again, that's not singular. The thing doesn't reflect the singularities. So what Armgren does is in that case is then you're forced to do this. Take out the average, remove the average, and look at the difference. Okay, and this is where the center manifold comes in. And that is by far, this is one of the sort of the most complicated parts of Armgren. However, with quadratic decay, this is not so bad. This is, well, it's still complicated, but that's a good case to focus on. Okay. Why is quadratic decay good? Well, Armgren's construction has very nice properties. If you had a branch point with this particular estimate at the top, if you can prove this estimate uniformly for every quadratic decaying or every branch point, let's say, and then look at the quadratically decaying ones, then the center manifold corresponding to any such point, it will be a sufficiently regular graph over the plane, tangent plane, and then it captures all nearby quadratically decaying points, of the same density. Okay, that's a very good starting point, right? You can then understand the current, try to parameterize the current over this center manifold to look at the difference of sheets, right? So that's what the second bullet point says. There is a normal map that parameterizes the current as a multi-valued graph, approximately, but very good approximation with estimates on the errors. And this center manifold remains well-centered all the way to all the quadratic points in a uniform way, right? If you had this estimate. So in a whole neighborhood, you have this normal map now, which it's just generally Lipschitz, but at the quadratically decaying points, there's enough decay to say that the critical set contains these quadratically decaying points. So now we are in a situation where you have quadratically decaying branch points contained in a map which satisfies certain variational principles, and in whose critical nodal set contains the set you're trying to study. You see, we are getting from geometry to more like a PDE problem here, right? And then that's absolutely fantastic. This very powerful discovery of Armgren's, the Armgren frequency function corresponding to this map N is monotone, approximately monotone. So that's the tool, right? We have a PDE kind of problem to study. Now here Armgren provides this tool to study that with monotone frequency function. And we're trying to understand the critical nodal set. And that's a sort of a classical kind of a PDE style thing. And this is because you can move from one quadratically decaying point to another very freely with uniform estimates. This is a very good point to be in, okay? I'm not saying all this is trivial. This is still a lot of work, but you are in a situation that is actually very canonical. So we, for lack of a better word, we're going to call this canonical case of the center manifold, okay? And I've written down the center manifold, the frequency function formula here, but don't worry about that. You don't need to sort of remember this. It's just energy over the height. And in Armgren's version, Armgren didn't have this cutoff function. It's just energy and then height over the boundary integral over the boundary of the ball. But this observation that you can build in a cutoff function is very nice and very useful, and for us for later on. is due to delay and Spadaro. It's the same calculation that Armgren does, but you can keep that in so you can avoid having to deal with boundary integrals, for example. We will in the next couple of slides, I'll show you a geometric frequency function designed to essentially playing a key role in improving uniqueness estimate for the branch set. In that geometric, we will call it planar frequency function. Having this cutoff function, we're going to borrow that technique. That's actually very, very useful. So anyway, moving forwards. So now, that's a major assumption I make, right? We have not only a decay estimate, the decay is quadratic. So to take full advantage of this canonical case, one has to have a way of analyzing all other branch points some other way, right? Ideally avoiding center manifolds. And our contribution to the subject is that you can do that. The only case in our whole program where you need a center manifold is the canonical one. But if you, again, going back to Armgren, in this classical Armgren's approach, the approach is to somehow to make this center manifold work no matter what, right? For every branch point. So this means that one has to construct a iterative process for every branch point, a sequence of center manifolds. None of them is capturing any branch point. There's no guarantee that it'll go through any branch point. and so that's it technically is quite demanding, that process. But one can avoid that. And so we didn't start out by trying to simplify Armgren. But somehow we are coming to this from the point of view of understanding the local structure, right? See, from that point of view, reducing to this canonical case is extremely helpful, if not imperative, because if you keeping track of these sequences of center manifolds and uniform estimates, at least we don't really know how that could work. But so for us, it's a necessity essentially to be able to only rely on the center manifold when you absolutely need it with these extra properties. Okay, so here's a list of our results. Okay, so let's just maybe go through this, and then I'll try and. So my goal is to try to get us to maybe a first couple of them. And then Brian will take over and do the rest of it. So first is that we get uniqueness of tangent cones at hn-2 almost every singular point. So these tangent cones are supported either on a single plane if you had a branch point, or on two or more planes meeting along an n-2 dimensional subspace. Okay, this is what happens at a typical point, meaning hn-2 almost every point. And this is proved without the use of the center manifold at all. Even the canonical case is not needed for this. And that's not an unreasonable expectation if you think about it, right? Because, as I said, the point of the center manifold is to look at the sheet separation, keep the sheets separated, right? See, from if the premise is to understand the dimension directly without anything else, that is essential. You need to keep the sheets separated, right? You need to see the singularities. But if you're trying to prove uniqueness as tangent cones, sheets coming together rapidly towards each other is a good case, right? So we let that infinite order decay possibility open, right? That's fine. We're going to focus on uniqueness. And once you have these estimates, especially because they are uniform, then that's going to help with the center manifolds. Mm-hmm. Okay, so that's tangent cone uniqueness. And then with that, as I said, the singular set size now parts of Armgren's thing can be simplified. A more geometric proof gives us a dimension bound. And then right, I have to really emphasize that it's really only part of Armgren's that we simplify. We really rely on many of Armgren's key ideas in the whole program. And then higher order. So this is number 3 is our kind of the main result. If you from a structural point of view, this number 3 is the key, really. And this, in terms of techniques and so on, this relies heavily on methods that Leon developed in the mid-90s, and we extend this to this higher multiplicity setting, and also in my stability paper, we some extensions earlier. So from this point on, high order asymptotic structures, singular set, topological conclusions, those things all bring Leon's ideas into the picture very much. So what does it say? It says that at a typical branch point, where we know that there's a unique tangent plane from above the previous results. So not only that, this says that the tangent function, so if you do a rescaling and rescale more in the vertical direction by the L2 height axis, you get a unique multi-valued harmonic thing. Okay, and the explicit, this is a very explicit form. See, it splits off a direction and -2 translation invariance. So it's a two-dimensional multi-value thing. So very classical branched harmonic function, Q value. Okay. Now, once you have a correct frequency function to do this with, it is easy to see that you always produce non-trivial tangent functions. But what can happen is that it may depend on the sequence you took for rescale, right? It may rotate. But the uniqueness says that there's only one, and with an estimate. And because it is classified this way, so before you prove uniqueness, you can get the conclusion easily, like I said, with the frequency function, that you get, or you can classify them, all the objects, and this is the list. They all look like this. Now, tangent cone uniqueness is generally an important and fundamental question to address in any kind of singular set analysis. It is especially motivating to study the uniqueness problem when they are classified. So very literally, if you can write down what they are, then it's very tempting to understand the uniqueness question, right? Because it is going to tell us quite a bit about how the nonlinear object behaves as you come into the branch point. And so that's the motivation. So to understand the structure of the current and the topology, hopefully, our approach at least is to prove uniqueness to this tangent function. Again, that's true at almost. So you pick up the next order term if you think in terms of a Taylor expansion at the branch point. This is just picking up the order beyond 1, right? There's in fact a gap, right? 1 plus something here, the decay rate. Now, but this is very subtle, I should say, because remember that example that I showed, the thing that has a jump in the frequency and therefore non-trivial topology, that shows you that just because, as you rescale, at the linear level, you might get a disk, which you always do as I've written down here. Doesn't mean that information directly transforms into the current, right? You do need this extra condition on the frequency to get the topological conclusion, and that's number 5 actually. That's how you prove the disk theorem under frequency not jumping condition. And then so you get 2 things: the topological conclusion as well as the structure of the singular set out of this higher order asymptotics structure. Our structure theorem says that the singular set is locally a finite number of pieces, each having each n-2 rectifiable with locally finite measure. Okay, this is Leon's conclusion. In fact, remember I said in very different methods of it. We don't none of this doesn't subsume Leon's theory. Actually, these are completely different methods in multiplicity 1 classes that Leon studied, but you come to the same conclusion. Right. So before we move on, I should mention that Delilis, Minter, and Skorobogatova have independently established almost everywhere uniqueness, our conclusion 1, and part of conclusion 4. They've established countable rectifiability of the singular set, which is part of our conclusion 4. And again, their methods are different. They rely on basically where Armgren left off, this iterative construction of center manifolds for each branch point, and then also their method for countable rectifiability is via proving upper Minkowski content bounds for the branch set, not via uniqueness of blow-ups. And then Shenghua Liu has examples that show that as a general conclusion, the rectifiability is essentially the best you can say about the structure of the singular set. Now, again, just two kind of philosophical remarks here. Our approach is somehow we obtain this by, as I kind of indicated, via a uniform, sort of a unified approach, because we feed, so tangent cone uniqueness question is central to everything, in particular, including the dimension bound. So these are tied together, all of this. And then higher order asymptotics is kind of the main result. And then from that, you get these other things, right? So this program is structured that way in a sort of a uniform way. And then everything is based on estimates, uniform estimates. And this is, again, as I indicated earlier in the lecture, that this kind of aligns the high codimension theory more closely with, at least in spirit, with codimension 1 regularity. But the way you prove these estimates are quite different. In codimension 1, you linearize and you look at estimates for harmonic functions and then transfer to the surfaces. But that's not the way it goes here, at least in our proof. These are more frequency function based methods, frequency-based methods. So planar frequency. This is a sort of a geometric frequency function we introduce in this work. And I know I'm running out of time, I guess. So this again, don't worry about a particular form. If you know the frequency, you'll immediately recognize what this is, at least sort of a PD sense, and you might understand. But if not, if you're not in the subject, then just kind of listen to me rather than trying to memorize this. But anyway, very quickly, what this is, the definition is that at the bottom here is the frequency function. It's a function of a real variable rho. So rho is between 0 and 1, let's say. Take a plane P, fix that. Let's assume it's Rn. We can always rotate things. And you have your current, which we are going to assume is sitting in a cylinder over that Rn of, let's say, radius 2, and has no boundary in in that cylinder, a current boundary, and doesn't go off to infinity in the cylinder, okay, in a bounded region. And then we define these two quantities, d and h. D is in the classical frequency, this is the energy term. If you had a function, this is for classical harmonic function, this is the Dirichlet energy. But here is the tilt axis. This is everything is, so this is defined without any parameterization on the current, right? The definition makes sense. Integrating on the current with respect to the measure on the Grassmannian here. Ignoring the orientation, right? This is defined for Bauer force. So it's the tilt here, plane, fixed plane, that's the pi p, is the projection to the fixed plane, and pi s is the variable plane, and that's, you're measuring the tilting. That's d, and then scaled correctly. And then this other thing is the height, right? Height with this extra factor. This factor is there because of the nonlinearity. Helps to control error terms and so on. Then we've also built in this idea of keeping the cutoff function inside, right? Coming from Dillellis and Sbararo earlier. So that's our frequency function. Okay. We will call this the planar frequency function. It's well defined as long as h is non-zero. And it's geometrically defined on the current. There's no need to parameterize. Now, the theorem says that if the current is decaying to the plane, so again, choose the plane P, assume the current is decaying, potentially extremely slowly, but still positive alpha, okay? So that's polynomial decay. Don't need quadratic or anything, just any decay would suffice for this. Suppose the decay holds from 1 to some value. We're not assuming decaying all the way to 0 at this point, just any interval. And as long as it's decaying, this thing is monotone, the plane frequency, or approximately monotone. In particular, it's bounded. Okay? So that's the theorem. And notice that again, we are trying to do two things at once here, right? We wanted to prove uniqueness of the tangent cone. And we assume decay, and then we first prove monotonicity of the frequency. Okay. And then we use that to prove decay at the end, conclusion. So we are marrying these two things together. Decay, proving uniqueness of the tangent plane with a uniform decay estimate, and proving there is a monotone frequency function. You get both these things at the same time at the end. At least almost everywhere. Okay. And then another extremely useful fact about this definition is that this is easy to check, is that if you have a cone, no matter what, whether it's close to a plane or not, there's no assumption about it being close to a plane. If the current is a cone, then the planar frequency takes values, it's constant, and if the base point is the origin, constant is less or equal to 1. Okay, this is very useful. Okay, so with this, hopefully, okay, goodness, time-wise. So let me now, okay. Let me maybe try and get to the decomposition theorem I promised at the end, right? So remember, Almgren has branch versus non-branch split. It's a qualitative split. And let me now discuss a quantitative way to decompose a singular set into two pieces first, using the planar frequency. Okay, hopefully I can get us to that point, and then Brian will explain how to analyze each of those pieces. Okay, so we need a definition for this our quantitative decomposition theorem, which will be on the next page. But let's try to understand this definition. Pick a beta, small number, fix that, and then suppose you have an area, at this stage, anything really, it doesn't have to be an area minimizing current, but this current T. So this definition is for a base point Z and a scale rho. And the terminology we're going to use is beta non-planar approximation property. Okay. So we say that the current satisfies the beta non-planar approximation property at the point Z and at scale rho if the current is significantly closer to a cone that depends on possibly the point and the scale, cone C, than it is to any plane. Okay, so this if you look at, so on the left you have the two-sided L2 distance at scale rho from the current to some cone C. And on the right, you have the optimal distance it can have relative to any plane. Okay, this plane passing through that point Z. So look at the ratio, and we want that ratio to be small. Okay, beta is a parameter at this point, but imagine it being extremely small. So the current is now going to look, if it satisfies this property, more or less, more like a kind of a non-planar cone than it is like a plane. But keep in mind that we are allowing, there's no assumption here anything is big. It's good. Both sides could be extremely small. Right? So if this property holds along a sequence of scales or some range of scales, as you go in, it could still be degenerating, but when if it does, it has to do so if this property satisfies at all scales, while being extremely much closer to a non-planar picture than it is to a plane. Okay, that you need to make. So there is, in this property, we are building in a certain amount of non-degeneracy, right? We are still seeing some kind of axis here. It turns out to be n-2 if these cones are. They're not necessarily always area minimizing, but nonetheless, one can check that in the theorem that they come with n-2 dimensional spine. So we are building into tangent cones need not be non-planar under this property if it holds all the way. Nonetheless, there is a certain amount of enough non-degeneracy to control the dimension. That's the point of these points where this property holds. Okay, so that's just a definition at the moment. Now here's the theorem. The theorem says that the singular, so imagine you have your area minimizing current, and suppose at some large scale but fixed. Okay, so this capital R is fixed depending on the Q, on the density. And then this beta, right? We're going to pick a beta, fix that, and then this is uniform capital R. At that large scale, suppose the mass ratio is not much more than Q. This will be true at a branch point of density Q, right? If you by rescaling, you can arrange that this hypothesis is satisfied eventually. And the conclusion is that in the smaller scale, which I've taken to be the unit scale now, right? R is big, 1 is small compared to R. At that scale 1, all points of density at least Q will split into two pieces, a script B and a script S. They are disjoint, these pieces, and they depend on the chosen beta. And so the conclusion says that part 1 is that if you have a point in S, then so S is characterized by the property that the point has density at least Q, and there is a radius depending on that point, rho naught, such that the current satisfies the beta non-planar approximation property at any nearby point, uniform. See, this is uniform now, right? At every point, you're allowed to move Z to any point in that rho naught neighborhood about Z naught. At any point of density at least Q. And here's the important thing, at all scales all the way to 0, you are going to preserve this beta non-planar approximation property as you go in. This could be a branch point. I have to emphasize this. Right? Nonetheless, you have a bit of non-degeneracy here. Okay, that's what goes on in S. S is characterized by that, and the theorem guarantees that if you're not in S, it's a unique tangent plane and a uniform estimate. That's all that's true, right? And the alpha, the rate of decay doesn't have to be quadratic. That's too much to expect, but something is fixed. Okay, and again, the decay holds all the way. This is a genuinely uniqueness statement, right? Along the B set, now they are all branch points, but not only that, they come with this estimate. Okay, and the planar frequency obviously then kicks in. The planar frequency theorem says that if you have decay, you have monotonicity. You can pass to the limit. Planar frequency value is at least 1 plus alpha. So there is a gap. It's not allowed to be 1. Okay, along B. Okay, so this is our decomposition theorem. So one or the other has to hold, right? So you see this split, they both come with estimates. For second half, very strong estimate, very good starting point to analyze the set B. Uniform estimates, you can move along B however you please. And on S, we have this initial non-degeneracy condition, right? Again, locally uniformly. The way the planar frequency plays a role in this theorem is very quickly in one line, so I don't have the time to explain the whole argument, is it prevents the current from oscillating between these two scenarios, right? That's what you worry, right? It may be close to this non-planar picture for a while, and then decide suddenly and start to decay, and suddenly decay rate can go up and up and up as you go in. Planar frequency says that can't happen, right? If you are in S, your planar frequency value is nearly 1. Remember, planar frequency is well defined without any parameterization, geometrically defined. So that if you can compute what it is when you're near a cone. The value at the cone is 1. Remember that I said that that's an important fact, right? It's no more than 1 on cones. Therefore, when you're near a cone, it's easy to check that it's not much more than 1. So if that's the case, then it's going to remain like that for a little bit, no problem. But the planar frequency then, if it starts to decay, then the planar frequency monotonicity theorem applies. It tells you that the planar frequency will remain not much more than 1. So you cannot go rapidly, suddenly fast, right? It has to remain locked in that planar frequency nearly 1 case. And that keeps you in the category of set S all the way, if it happens. Otherwise, it can decay fast and you're in B, right? That's how it goes. And then single set dimension bar, let me just maybe go through this and I'll probably stop. Keep in mind that this set, so remember this the classical split of non-branch points, meaning that no tangent cone is a plane, it's easy to check that that's actually in S. Right? So S is, in principle, it's a bigger set. It can have branch points, it can be a huge branch set at this point. So it contains this S arm, but it has this non-degeneracy, and therefore the bounding the dimension of this is actually just as easy as you do for S arm. The same argument, in fact, that part. Okay, you got to be careful because everything depends on beta, but this estimate is easy to check. This n-2 plus gamma beta measure of S beta is 0, where gamma tends to 0 with beta. And then step 2, we need to prove the same, and I'm talking about the dimension bound, right? The same bound for the B, where we split B into 2 pieces. Planar frequency exactly 2 points, and planar frequency not 2 points. Planar frequency makes sense now, right, on B, because we have decay. If the planar frequency is not 2, we don't need a center manifold. We just take one simple blow up. This is a kind of a standard use of frequency function. You see either splitting into a singular thing, or if it comes together, you see an axis. If the planar frequency is not 2, and the singular points concentrate near the axis. And that's all it takes to bound the dimension, right? So the only case you need a center manifold is planar frequency exactly equal to 2. And that is a canonical center manifold, and that is how that part is handled using that. And then putting all together, you get the dimension bound. Okay, so I think I should stop here. Thank you very much. Sorry, I went over. Sorry, Brian, your time.
Any question?
Maybe we should save questions until Brian has finished then.
Yeah, so let's continue the second half. Do you need?
Oh, no.
Yeah. So let's continue the second half by Professor Krummer.
Oh, does this work? Okay. Is this working now? Okay, good. I'd like to thank the organizers, including TSL, for inviting me to speak here. This has been my 3rd time to China in the last 2 years and my first time to Beijing. So I'm hoping this is the beginning of many other visits to come. Also, I'd like to wish Leon happy birthday. Leon is, of course, a brilliant mathematician. His work has influenced what I'm about to talk about shortly. And also, Leon is a brilliant communicator in mathematics and has been highly supportive of my career. As Nishan pointed out, he introduced me and Nishan when we went to a sabbatical in Cambridge when I was a PhD student. And he's been very supportive of our work since. And also, as I pointed out, I'm messing this up, sorry. But yeah, he's really good at communicating very deep mathematics in a very clear way. And in fact, you have a little bit of a fan group at Melbourne. My master's students have been watching your lectures of your GMT lecture notes online. So thank you so much for being such a great mentor and your support. All right, so this is a continuation of the previous talk. And so I more or less will start where we just left off. So Nishan discussed a few minutes ago about how if we consider an n-dimensional area minimizing current T and the set of density Q singular points, we can decompose the set of singular density Q singular points into 2 sets, S and B. And so S is the set of density Q singular points at which there's a non-planar approximation property such that for every point Z0 in S, there exists a radius sigma, which in particular is a uniform radius. That's the key point here. So there's a uniform radius associated with Z0, such that for all of the singular points Z of density Q near Z0 and all uniformly small radii rho, in the ball of radius rho centered at Z, T is significantly closer in L2 to some non-planar cone than T is to a plane. And note that this is much stronger than what you naturally get from the monotonicity formula for area, which would merely say that in the cone, in the ball, T is well approximated by a cone, possibly a plane. And then B, of course, is the set of branch points of what we call alpha rapid decay. So if Z is in BQ, that means that there's a unique tangent plane, which I'll denote by PZ. And T will decay to the unique tangent plane at a rate basically radius to the power 1 plus positive alpha in terms of L2 distance. So one of our first big results is that if T is an n-dimensional area minimizing rectifiable current, then T has unique tangent cone at almost every singular point Z and T. So this is with respect to the n-2 dimensional Hausdorff measure. So Almgren's big regularity theorem says that the singular set's n-2 dimensional. So they're saying basically, except for a set of measures 0 relative to the correct dimension, there's a unique tangent cone. And so in particular, if we represent the density Q singular points as S and B as on the previous slide, then there exists at almost every singular point in S a unique tangent cone, C sub Z, which is supported on a finite union of 2 or more planes, such that the planes intersect along an n-2 dimensional linear subspace. So in particular, they have an n-2 dimensional axis. And then along the way, just as a consequence of the method of proving the uniqueness of tangent cones, we get for free that SQ is n-2 rectifiable and in particularly has locally finite Hausdorff measure. Now notice here that as Nishan emphasized, S could contain branch point singularities, at least in principle. In fact, it remains open whether S contains any branch points. But what the first item here says is that if there are branch points in S, they must be in S on a set of measure 0. So in particular, being a branch point of alpha rapid decay is typical of branch points. And if you recall from the previous slide, at every point in B, there's a unique tangent plane. And the crucial thing here is also that not only do you get uniqueness of tangent cones, but we get a decay estimate where T decays to unique tangent cone inside the ball radius rho centered at Z at a rate radius to the power a positive power mu once you do the right scaling for the L2 distance. Right. All right, so this is going to use a blow-up method which was introduced by Leon Simon for multiplicity 1 classes of minimal submanifolds. So multiplicity 1 class is a class of minimal submanifolds which is closed under rigid motion, scaling, and weak limits. And in particular, every minimal submanifold in the class has multiplicity 1 on the regular set. So what this means, amongst other things, is if I have a minimal submanifold in the class, every tangent cone to points of the minimal submanifold are in the class. And in particular, since the minimal submanifolds in the class have multiplicity 1 on the regular set, if you have a tangent plane, you only have a multiplicity 1 tangent plane. So this rules out branch points. Now, 2 years after, so this result was introduced in 1993. 2 years later, as Leon told me, Leon proved another major result where he showed if you have a minimal submanifold in multiplicity 1 class without an integrability hypothesis, the singular set's rectifiable. And this applied to a wide variety of elliptic problems, including harmonic maps. So that sort of overshadowed the 93 work for a while. And then later on, Nishan, when he started with his thesis work leading all the way to his 2014 Annals paper and some other work of his, Nishan applied the blow-up method to to stable minimal hypersurfaces. And so in particular, the big contribution Nishan introduced is a way to apply the blow-up method in higher multiplicity settings. And so from there, there became incredible interest in applying the blow-up method to a wide variety of problems in geometric analysis. One of the results that used the blow-up method is my joint work with Nishan, in which we considered branch point singularities of Dirichlet energy minimizing multi-valued functions. So it's a class of multi-valued harmonic functions, which arise as the linear problem for area minimizers. And we also looked at two-valued minimal, C1 mu two-valued minimal graphs. So the key innovation there was that we applied the blow-up method, but when Leon initially applied the blow-up method, he applied it using the monotonicity formula for area, whereas in our work, say, on Dirichlet minimizers and minimal graphs, we applied the blow-up method to study branch points via the monotonicity formula for frequency functions. So broadly speaking, what the blow-up method gives us is that under certain hypotheses, including an integrability hypothesis, if T is weakly close to a minimal cone, then T decays to unique tangent cone at almost every singular point of the right dimension or the top dimension. And moreover, the singular set's rectifiable. If, on the other hand, we have some stronger hypothesis, namely rolling out what we call delta gaps, then what the blow-up method gives you is epsilon regularity results, where if T is weakly close to a cone, then T is a C1 mu perturbation of the cone. And so this in particular applied in Nishan's Enel's work in 2014. All right, so the hard part in extending this work, or this method to area minimizers is firstly getting the decomposition into the sets S and B. So in Leon's initial paper, that just followed from the monotonicity formula for area and a compactness argument. Whereas, as Nishan explained, this very much relied on introducing the monotonicity formula for planar frequency functions. Moreover, another hard part, as I'll explain very shortly, is getting pointwise estimates for the current in order to show that if T is weakly close to a minimal graph, then away from the axis of the cone, then T is uniformly close to the minimal cone. Is there a problem? Okay. All right, so our main pointwise estimate is the following. Let's let P and Q be positive integers, and let's let kappa be a positive constant. So T is an area minimizer in the unit cylinder, which is weakly close to a plane, which we can rotate to be Rn with multiplicity Q. And then we're going to consider a current, bold P, which consists of finitely many oriented planes Pi. And Pi are all going to be close to Rn. And then we have this estimate here, which basically says the following. So I've oriented planes, so they have an associated n vector vec Pi. And I can think of vec Pi as like the slope of the plane. So then if I take the difference of the slopes of the two planes, take the distance, then that's bounded above by a constant times the minimum distance between the two planes in the cylinder. So then what this means visually is, firstly, if on the right-hand side I have 0, so the two planes intersect at least one point, then that would mean that the slopes have to be the same. So the planes have to coincide exactly, because then they have the same slope. Secondly, if I relax that a bit and still had a positive right-hand side, then as the planes get closer and closer together, their slopes get closer and closer together. So these planes are nearly parallel. So then our conclusion is, if you consider the uniform distance of points in T in a smaller cylinder to the support of bold P, that's bounded above linearly in terms of the L2 distance of T to P. So this is sort of what we would expect, for instance, from standard elliptic estimates. We might want to bound the suit norm above by the L2 norm. Now, in the case that there's exactly one plane, this is actually a classical well-known result due to Allard, in particular, which actually applies to stationary varifolds and also to varifolds with suitably small generalized mean curvature. And the proof basically follows from de Giorgi-Nash-Moser type argument. Now, if we have two or more planes, even for stationary varifolds, it's not known whether you get the linear bound as on the previous slide, but you can easily use the monotonicity formula for area to show that there's a sublinear bound. So you bound the uniform distance of T to P above by the L2 distance to the power 2 over n plus 2, which is less than 1. Now, in order to apply the Beaupet method, it's important that we get the linear bound. So I'm not going to go through the proof of the bound on the estimate on the previous slide, but sort of the philosophy of how we apply the estimate from the previous slide and also how we prove it via an inductive argument is that if the planes pi are nearly parallel and they're well separated, that is, they're much farther apart than the L2 distance of T to P, then T separates into area minimizing components uniformly close to each of the planes pi. All right, so there's this L2 distance that Nishan introduced in the previous talk. Just very quickly, if I have an area minimizing rectifiable current T and minimal cone C, and so for the next few two slides, we'll consider minimal cones, which are union of two or more planes and intersect along 0 cross Rn minus 2. And so then just as notation, I have this two-sided L2 distance, which is Q of T, the cone, and a ball. And so it has two aspects. The first term is the L2 distance of T to the cone. And the second term is the L2 distance of the cone to T, but in a smaller ball and outside of a tubular neighborhood of the axis. So very roughly speaking, one could consider this as like an L2 version of a Hausdorff distance estimate. And so in particular, it's a distance between the supports and doesn't quite account for multiplicity. All right, so let's fix that integer q, and let's consider a radius theta less than 1/4. Then there exists epsilon delta beta, such that if T is an area minimizer in the unit ball, and C is a minimal cone, as I explained before, and I assume that T is weakly close to the cone, in the sense that T has 0 boundary in the unit ball, so that implies that this varifold associated with T is area stationary. There's mass bounds where the mass of T in the unit ball is close to Q, and the L2 distance of T to the cone, the one-sided L2 distance, is small. And then we introduce this additional technical assumption, which says that T is much closer in L2 distance to C than T is to any cone C prime, which is a union of fewer planes, fewer distinct planes. So this last hypothesis, this is introduced due to higher multiplicity. You can relax it a bit. In particular, so this in particular says that T cannot hop between the planes of C. And you can relax it to say that T is much closer to a cone than it is to a plane, but then you have to introduce finitely many theta. So for instance, you've seen the proof of Allard regularity. In that proof, you have exactly 1 theta, and then you do an excess decay argument. Here, if you have finitely many thetas, that doesn't hurt doing the standard excess decay estimates. So then either there's a delta gap where there's some ball centered on the axis within radius 1/2, such that this ball radius delta does not intersect the set of points of density greater than or equal to Q for T. Or there exists a rotation and a new cone C tilde, such that the L2 distance of T after rotating to C tilde at scale theta improves by a factor of C mu to the C theta to the mu compared to the L2 distance of T to T in the unit ball. And so notice that C and mu are independent of theta, so this is a small decaying term. Now, actually, let me go to the previous slide. Now, notice that if I take the origin and I iteratively apply this excess decay lemma, and at every step I get alternative B, Then the standard thing is this would give us uniqueness of tangent cone at the origin. And then you could prove this by translating the base point and also get rectifiability. Now we have to consider what happens if I iterate the excess decay lemma and then I reach a scale where there's a delta gap. So then we get a picture like we have here, where in red I have the set of points T with density greater than or equal to Q, and in this dotted ball here I have a delta gap. And notice that the red set doesn't pass through the delta gap, but the red set is concentrated near the axis of the cone. So then the idea would be from there is to do a covering argument where you cover the red set by small balls, but you miss the delta gap when you do the covering argument. And then the hope is that would lead to a loss in n-2 dimensional Hausdorff measure. But then if you recall what I said before, I mean, we want to then in each of the balls find a minimal cone that approximates T and then restart the excess decay estimate. But T could be weakly close to a plane inside the ball if we just applied the usual monotonicity formula for area type theory. So then the key point is that S has this non-planar approximation property, which says that when we restart the excess decay estimate in the smaller balls, T is much closer to a non-planar cone in those balls than T is to a plane. So then we can restart the excess decay estimate and then prove uniqueness of tangent cones. Also, just as a quick reminder, the key point here is that we did not assume that S is the set of branch points, non-branch point singularities. Rather, we assumed that S is just the complement of the set of branch points of alpha rapid decay. And then we deduced from that the set of branch points in S has measure 0. So for instance, rectifiability in our case is not just a corollary of neighbor-Bella torta. All right, how much time do I have from here?
Oh, so you started 10 minutes later, so maybe like still 20 minutes, something like that.
All right, we'll see how it goes. All right. All right, so now what I just covered was what we do to study the set S. What we now need to do is study the set B of branch points of alpha rapid decay. And so let's let T be an area minimizing current, as we've done throughout the talk. In particular, be a current of the unit cylinder with 0 boundary in the cylinder, and we'll assume that T is weakly close to Rn with multiplicity Q. And let's consider branch point Z in B, in particular in the cylinder radius 1/2. And let's just recall that we denote the unique tangent plane of T at Z by P sub Z. So then, as Nishan was explaining towards the end of his talk, what we proved is this monotonicity formula for what's known as the planar frequency function. So I've written it out here. At a quick glance, this might be a little bit of a mystery, but it's just, as Nishan said, the usual formula you would get, say, if you looked at frequency functions of harmonic functions. And in fact, it looks closely like the ratio that Rick mentioned in his talk earlier today, but with a ball in place of the manifold M. But in any case, the key point here is if I have T, a plane, and Z, the planar frequency function at radius rho tells us how rapidly T is decaying towards the plane P. But in particular, it indicates this only if I have an interval of radii where T is decaying towards a plane. So in order to get the decomposition into S and B, it was crucial that we allow for the possibility that T is decaying towards a plane and then reaches a scale where it's not close to a plane, and still have monotonicity of planar frequency on that range of radii. But now if we're studying points in B, we're in the good case, where now we're alpha rapidly decaying towards the unique tangent plane at every scale. So then for the full interval of radii from 1/8 all the way down to 0, we get that the planar frequency function is approximately monotone non-decreasing. Now, since it's approximately monotone non-decreasing, we can define the limit as the radius tends to 0. So I should emphasize this is the planar frequency function relative to the tangent plane. So now we know that the planar frequency function relative to the tangent plane is monotone non-decreasing. So as we let the radius go to 0, we get a limit, which is called the planar frequency of T. And then another thing we can do I've written out in some words here, but just to briefly explain, what we want to do is be able to blow up t relative to the tangent plane. So if t was literally the graph of a q-valued multi-valued function, what you would do is translate z to the origin and rescale by 1 over rho horizontal to the plane. And then, since t is decaying towards a unique tangent plane, you scale by even more by dividing by the L2 distance to the plane, and you scale even more vertically relative to the plane. And then you pass to a limit, and you get a limit, which I'll call phi. And so that's called the tangent function of t at z. Now, in general, for area minimizers, you don't know that t is identically a q-valued Lipschitz graph, but there is a Lipschitz approximation theorem, and so that's how you can implement this construction. And so then we get a limit blow up phi of t relative to the tangent plane, which is non-zero, homogeneous of the degree of the planar frequency, and is Dirichlet minimizing. And then, as Nishan pointed out in his talk, at almost every point in B, in particular with planar frequency not equal to 2, there's at least one tangent function which is cylindrical. So that means once you choose coordinates on your tangent plane, it's a sum of components with integer multiplicity. One component might be 0, and the other component is the real part of c x1 plus ix2 to a power. The power is the planar frequency, and this planar frequency in lowest terms is a rational number which in lowest terms the denominator is less than or equal to the density. So then the fact that we get this explicit form for the tangent function suggests that we can apply the blow-up method to prove uniqueness of the tangent functions. And so as notation, let's focus on the set of branch points b not equal to 2, consisting of branch points with planar frequency not equal to 2. And then the complementary set will be b equals 2, so that's the branch points with planar frequency equal to 2. So regarding the results for b not equal to 2, for every compact set k in the cylinder radius 1/2, which does not intersect the frequency 2 branch points, b not equal to 2 intersect the compact set is locally a finite union, finitely many pairwise disjoint, locally compact, locally n-2 rectifiable sets. And in particular, they have finite n-2 measure. There's a few different ways to state this result. In particular, the reason I stated things here, in particular, so that k does not intersect b equals 2, is since the set of points of planar frequency strictly bigger than 2 is not necessarily locally compact. The next result is that for with respect to the n-2 dimensional Hausdorff measure, at almost every branch point z in b not equal to 2, there exists a unique cylindrical tangent function, phi upper z. And this comes with a decay rate where the t is decaying to the graph of the tangent function in terms of L2 distance, like radius to the power of the planar frequency plus a positive power. Furthermore, if z is in b not equal to 2 and is a good point where we have the planar frequency is well defined and it's not equal to 2 and we get a unique tangent function. And moreover, the planar frequency is equal to a rational number p over q, where q is the density of t at z. And so then if I also take a suitably small radius rho, and I know that inside the ball radius rho centered at z, z is strongly, n-2 strongly non-isolated. So this means that I take there exists an n-2 dimensional linear subspace L, such I can do the following. I take B, and I consider the points of planar frequency greater than or equal to the planar frequency at Z. Then I translate Z to the origin, and I project this portion of B onto the linear subspace L. And so then I'm strongly non-isolated if the projection onto L contains a ball centered at the origin. So in this case, we state it as the ball of radius rho over 2. So then So this hypothesis that Z is strongly non-isolated, morally speaking, what it does is it tells you that this tangent function at Z has to be cylindrical. And moreover, it tells you that you can roll out delta gaps. So then what you can conclude is that the support of T near Z is homeomorphic to an n-dimensional ball. So then, in particular, after translating so that Z is the origin, the tangent plane at Z is Rn, and rho is 64, just for convenience. Then the singular set inside a singular set near Z is parameterized as a graph over the axis of the tangent function. So as g of y, y, h of y. The support of T has a specific parameterization. So it takes the form g of y plus z to the q y f of zy. Now this g of y, that appeared above. So that's because we're centering things on the branch set. So then if I ignore the g, this is basically like z to the power q, y, f of z comma y, where z is a complex variable. And so this is somewhat analogous to, for instance, what is obtained in McAuliffe-White. And in particular, we get asymptotics where f up to leading order is like the real part of cz to the power p. We have bounds on the sup and the sup norm of the derivatives for the error term, which they decay at a rate faster than z to the p. And we also similarly get if I take a root of unity nu not equal to 1, so qth root of unity, f of zy minus f of nu zy as a leading order term, real part of a z to the power p with decay estimate. And so the key point here about these asymptotic expansion here is that this gives us an asymptotic expansion at the origin, which is directly analogous to McAuliffe-White. And right. Now, the key thing that we need in order to prove all of this is our analysis of B not equal to uses, again, the Leon-Simon blow-up method. So we first have to get point-wise estimates. And I'm not going to write down the point-wise estimates, but they're point-wise estimates for T relative to the graph of the relative to a union of nearly parallel graphs of single-valued harmonic functions. And then we also have to adapt the blow-up method, replacing the monotonicity formula for area with the monotonicity formula for planar frequency functions. So in particular, let's let T be a rectifiable, locally area minimizing rectifiable current of the unit cylinder, which is close to Rn with multiplicity Q. And let's take a cylindrical tangent function of degree Q, or degree alpha. And as before, let's assume that T is significantly closer in L2 distance to the graph of phi than T is to any cylindrical function with fewer non-zero components. And so then the final thing we need to assume is that the origin is in B. T is tangent to Rn at the origin, and the planar frequency is greater than or equal to alpha at the origin. So then we get the following estimate, where here we're going to let R be the horizontal radial distance parallel to the tangent plane. We're going to take the tangential gradient of R dot the tangential gradient of the height relative to the tangent plane divided by R to the alpha. And we're going to represent this as an L2 integral. And this is bounded above by an axis with two terms. The first term is the L2 distance of T to the graph of the cylindrical function. And the second term is the L2 distance of T to the tangent plane. But notice that here I have an L2 integral for the left-hand side and the first excess term. But here I have a power of to the power 2 plus a positive number sigma. And so in particular, this quantity, last quantity, shows up because the minimal surface system is nonlinear. And it will, when you apply the excess decay type arguments, this part of the excess is automatically decaying. So then the principal term here is the L2 distance of T to the cylindrical function. All right, so then if, now everything I said so far, it just concerns the analysis of S and B not equal to 2 and does not involve Holmgren center manifold. if I want to consider the set of points of planar frequency equals to, as Nishan indicated, we have to use Almgren's center manifold. But this is precisely the canonical setting where near a point Z of planar frequency 2, we construct a single center manifold, M, which passes through Z, and so that all the nearby frequency 2 branch points near Z are in the center manifold. And so then this avoids the need for constructing an infinite sequence of center manifolds as occurs in Almgren's work, as well as Della Spadaro and Della Smitner Skorba-Gotova. Now, in order to then, all the results I've already mentioned on the prior slides, they extend to the set of points of planar frequency 2 in place of B not equal to 2. Except when we compute frequency functions and blowups, we do so now relative to the center manifold rather than the tangent plane. Also, the results actually extend to the points of planar frequency greater than or equal to 2. So as one final slide, what this gives us ultimately is the following result, where if T is an n-dimensional area minimizer in an open subset of Euclidean space, then at almost every branch point, T has a unique tangent plane, PZ. There's a quantity called the branching order, which quantifies the rate at which the sheets of T are separating. And in particular, it equals the planar frequency at Z when the planar frequency is less than 2, and it equals Almgren's frequency relative to the center manifold if the planar frequency is greater than or equal to 2. Moreover, there exists a single valued function psi, which is whose graph is either psi is 0 if the planar frequency is less than 2, or psi's graph is just the center manifold when the planar frequency is greater than or equal to 2. And we get that psi is asymptotic to a homogeneous harmonic function h at the degree of the planar frequency. T is asymptotic to the graph of psi plus unique non-zero tangent function phi z at the order of the branching order. And the center manifold, that is psi, is essentially unique up to the order of the branching order. So if I had another psi tilde that worked, then psi tilde minus psi in L2 differs by little o of the radius to the power of the branching order. All right, so thank you very much for your attention.
Any questions?
Yeah, quite a technical tour de force. Thank you. This is already complicated enough, but let me ask a question about possible future directions. Do you think that there's any chance of getting similar rectifiability results for the Almgren strata, lower dimensional strata?
I have not thought that through yet. Yeah. That's more complicated because
way more.
Yeah. Because then you can have branch points away from the axis with I haven't thought about it, but if I wanted to work on it, I'd probably start with dimension 3 or something.
Yes. Yeah. But sometimes these things can turn out, it sounds impossible at the moment, but sometimes these things can turn out to be simpler than you expect in some sense. So maybe you should think about it a little bit at least.
Any other questions?
Yeah, thank you, Brian and Nishan. I have 2 questions, if you don't mind. So should we think about, so in your decomposition of the branch set, should we think about the branch set with frequency not equal to 2 as the ones whose frequency is more like 2 minus?
Oh, all right. So I try to keep things simple, but yes, that would be correct. In particular, that in the case that the planar frequency greater than or equal to 2 minus epsilon, you do get you can apply both approaches, the planar frequency function approach and also the frequency functions relative to the center manifold. The only thing is, if your epsilon is very small, then you're probably not going to have a cylindrical tangent function. You're in the lower stratum. Also, that is highly relevant to extending this to the Riemannian setting, because then you have to use what's known as a truncated frequency function, sort of like they do in for studying, say, the Signorini problem. And so then for that, you have to have the decay be less than 2. Slower, you want your decay to be slower than that of the ambient space.
It's a little bit hard to understand how come for 2 minus and 2 plus, you have the same results, whereas the same approach, whereas for different to 2, you need center manifold. Because I would imagine if you have 2.
Okay, so hopefully I didn't misunderstand your question. So if the planar frequency is close to 1, you just say that you're an S and you use this locally non-planar approximation property. If the planar frequency is strictly between 1 and 2, then you have to use the, then at least in our method, we use the planar frequency function. And so that's simpler because then you don't have to construct the center manifolds. All right. Now, if the center manifold admits all branch points of nearly quadratic decay, and then if your planar frequency is greater than or equal to 2, or even greater than 2 minus a very small delta, then you can apply, you can either consider, oh, sorry, I should say, if your planar frequency is strictly bigger than 2, then you have to apply, I see your point. You have to apply the, you can apply both approaches. When the planar frequency is exactly 2, that's where you have to use the center manifold. And that's because you don't want your blow up to be a single valued quadratic harmonic function with multiplicity. So that's where you need to force the sheets to be separate. Right. There's an analytical reason for it. The rough idea of it is if your planar frequency is less than 2, then when you blow up, your tangent planes in the blow up limit become horizontal. And that's relevant to semi-continuity. If your planar frequency is exactly 2, then that doesn't work.
I see. Thanks. Second question is, it seems that the final result, the decomposition into S and B, depends on the beta parameter. So is there anything that says, for example, the union of all S beta is codimension 2, or it's finite, it's H n minus 2 finite?
Yeah. So and sort of the reason it has to, of course, depend on epsilons and betas. But then once we study the, once we prove uniqueness of tangent cones, that requires fixing beta and epsilon small enough. And then, yeah, but you could approach it that way, that you let epsilon and beta go to 0. You might have to be careful about things like whether you break up into pieces that are locally rectifiable and things like that. But yeah, but in our method, we fix beta at some point, and then it goes from there.
Let's thank the speakers, and let's come back in maybe 13 minutes at 3:50. So the next talk is by Professor Zhou Xin due to the schedule change.